Long before the intricate instruments of modern astrophysics were conceived, the universe was already whispering its secrets through streams of invisible particles that zipped through space. These were the first hints at what we now call cosmic rays, a mysterious phenomenon that, for decades, puzzled and fascinated scientists around the globe. This chapter in the annals of science is a compelling tale of curiosity, perseverance, and the gradual unraveling of the cosmos's hidden fabric. To appreciate the profound significance of cosmic rays, we must journey back to a time when their nature was completely unknown, examining the initial discoveries, the experimental challenges faced, and the profound questions raised by these high-energy voyagers from the stars. It all began in the early 20th century, a time of remarkable progress but also profound scientific mystery. In the years leading up to the discovery of cosmic rays, scientists observed that electrical devices known as electroscopes, which detect and measure electric charges, were spontaneously discharging even when isolated from any obvious source of electricity. This puzzling observation suggested that some unseen, penetrating form of radiation was incessantly bombarding Earth. Initially, the prevalent assumption was that this radiation emanated solely from radioactive materials present in the Earth's crust. However, discrepancies in measurements at different altitudes and environments started to challenge this explanation. In 1912, an Austrian physicist named Victor Hess undertook a daring and pivotal series of balloon flights. Ascending to remarkable altitudes, some exceeding 5,000 meters, Hess carried sensitive electroscopes to measure the intensity of ionizing radiation. Contrary to the expectation that radiation levels would drop with distance from the Earth's surface, Hess observed that the intensity actually increased as he climbed higher into the atmosphere. This groundbreaking observation hinted that the source of this radiation lay not just in the Earth beneath, but originated from somewhere beyond our planet, from the cosmos itself. This discovery was revolutionary. It transformed an earthly mystery into a celestial enigma. Hess's work earned him the Nobel Prize in Physics in 1936, and it firmly established the existence of cosmic rays, a steady flux of charged particles arriving at Earth from outer space. Still, the nature, origin, and composition of these rays remained elusive, beckoning scientists to investigate further. The early work done by Hess was followed swiftly by additional investigations employing instruments on mountaintops, in caves, and deep underground. These studies revealed that cosmic radiation could penetrate significant depths and was not easily absorbed by ordinary materials, indicating extraordinarily energetic particles. Further study using cloud chambers, a technological marvel of the time that allowed the visualization of particle tracks, showed that these rays were composed mostly of charged subatomic particles, primarily protons and atomic nuclei, traveling close to the speed of light. The mystery deepened as researchers began to understand that cosmic rays were not merely an earthbound curiosity, but a fundamental element in the astrophysical processes of our galaxy and beyond. At the time, astrophysics was still in its infancy, and these high-energy particles provided one of the first direct links between observational phenomena on Earth and the dynamic processes occurring throughout the universe. Cosmic rays offered a unique probe into the energetic and violent events happening in distant astrophysical settings: supernova explosions, active galactic nuclei, and perhaps even more exotic cosmic accelerators. Through the decades that followed, the study of cosmic rays spurred technological innovations and methodological advancements. Early detectors evolved into sophisticated arrays distributed across continents, flying aboard balloons and spacecraft, enabling scientists to map the energy spectrum and arrival directions of cosmic rays. Importantly, this research also intersected with fundamental physics, helping uncover new particles and phenomena, challenging our understanding of particle interactions at energies unattainable by terrestrial colliders. Yet, even now, the story that began over a century ago continues to unfold. Despite vast progress, many questions regarding cosmic rays remain unanswered. How exactly are they accelerated to such phenomenal energies? What proportion originate from within our Milky Way, as opposed to extragalactic sources? And how do these particles influence the environments they traverse, including planetary atmospheres and star-forming regions? By reflecting on the dawn of discovery, the initial observations, the courageous balloon flights, and the emerging realization that the Earth is bathed in a cosmic rain of charged particles, we gain a profound appreciation for the blend of curiosity-driven inquiry and rigorous experimentation that defines science. This chapter of history is not just about cosmic rays themselves, but about the spirit of human endeavor to explore the invisible forces shaping our universe. As we proceed to the next stages of our exploration, we will delve deeper into the nature of cosmic rays themselves, examining their composition and energy spectrum, the diverse astrophysical mechanisms accelerating them, and the ongoing quest to understand their origins. From humble electroscopes that first discovered ionizing radiation, mysteriously charging and discharging, to satellites scanning the heavens for the highest energy particles, the unfolding story of cosmic rays is a narrative bridging the minuscule world of particles with the vast cosmic tapestry, revealing the universe in an entirely new light. As we transition from the story of the initial discovery of cosmic rays, we now embark on a fundamental journey to understand precisely what cosmic rays are. These extraordinary celestial messengers that traverse the vast expanse of space. To comprehend their nature, one must delve not just into their composition, but also into their energetic properties, origins, and the remarkable role they play in connecting the cosmos to our own planet. Cosmic rays are, quite simply, high-energy particles originating from outer space that relentlessly permeate the universe, continuously bombarding Earth from all directions. Despite the name, cosmic rays are not rays at all, such as light or electromagnetic radiation, but rather particles, predominantly atomic nuclei and subatomic particles that move at speeds approaching, and sometimes even reaching, a significant fraction of the speed of light. The majority of cosmic rays consist of protons, which are the nuclei of hydrogen atoms, making up roughly 90% of cosmic ray composition. Following protons, alpha particles, helium nuclei composed of 2 protons and 2 neutrons, comprise about 9%. The remaining 1% consists of heavier nuclei, stretching the periodic table from lithium all the way up to the heaviest elements, albeit with diminishing frequency. Additionally, a small fraction of cosmic rays includes electrons and positrons, as well as some gamma rays, but these are generally studied in the context of other astrophysical radiation processes. At their core, cosmic rays are charged particles. This electric charge endows them with magnetic interactions that significantly affect their trajectories through space, causing their paths to bend and twist through interstellar and intergalactic magnetic fields. This magnetic influence often obscures direct lines of sight back to their sources, challenging astrophysicists attempting to pinpoint exactly where these particles originated. One might wonder how these particles manage to possess such extraordinary energies. Cosmic rays span an enormous range of energies, from millions of electron volts, MeV, to astonishing ultra-high energies exceeding 10^20 electron volts, EV. To appreciate the scales, consider that the particles accelerated in the most powerful human-engineered particle accelerators, such as those at CERN, reach energies around 10 to 13, 39 to 10^14 EV. Cosmic rays, therefore, can be millions or billions of times more energetic, making them true natural particle accelerators. This immense energy allows cosmic rays to penetrate deeply into Earth's atmosphere, and, at times, even into Earth's surface. When these high-energy particles interact with atmospheric molecules, they generate cascades of secondary particles, further extending their influence and providing scientists with detectable signatures of their presence. The journey of cosmic rays toward us is an odyssey across vast interstellar and intergalactic distances. Their charged nature means they are constantly deflected by magnetic fields encountered along the way. These cosmic magnetic fields are pervasive and complex, ranging from the spiraling fields within galaxies to the tangled fields spread across intergalactic space. This intricate magnetic dance results in cosmic rays arriving at Earth from all directions nearly isotropically, creating what appears to be a uniform background shower of energetic particles. The study of cosmic rays has unveiled fascinating insights not only about their fundamental nature, but also about the environments they come from. Through careful measurements of their energy spectra, chemical composition, and arrival directions, scientists infer details about the astrophysical processes accelerating these particles. Some cosmic rays appear to come from relatively nearby sources within our Milky Way, while the highest energy particles likely originate from extragalactic phenomena, perhaps from active galactic nuclei, gamma-ray bursts, or other exotic cosmic accelerators still under investigation. Beyond their identity as particles, cosmic rays are veritable storytellers, carrying encoded information about the processes that forged and accelerated them. For example, the relative abundances of different nuclei reflect the chemical makeup of their source regions and the nucleosynthesis processes that occurred there. Measuring isotopic ratios and rare particle species helps decode pathways of cosmic ray propagation and potential interactions en route to Earth. These celestial messengers also tell us about the broader structure and dynamics of the galaxy. Through the diffuse glow their interactions produce in the interstellar medium, high-energy particles colliding with gas and dust, cosmic rays help shape the chemistry and ionization states of clouds where new stars are born. Their pressure influences the dynamics of galactic winds and contributes to the complex feedback loops governing the evolution of galaxies. Importantly, the discovery that cosmic rays are charged particles forced scientists to rethink fundamental assumptions about the universe and its contents. Cosmic rays introduced a new astrophysical component alongside electromagnetic radiation and neutrinos in our efforts to understand the universe. They also provided opportunities for high-energy physics experiments outside laboratory settings, revealing new particles and interactions that helped establish the foundations of particle physics. In modern astrophysics, the identification and study of cosmic rays continue to be at the forefront of research. Advanced detectors on the ground, balloons floating in the stratosphere, and sophisticated satellite missions traversing space all contribute to the continuous monitoring and characterization of these particles. Instruments such as the Alpha Magnetic Spectrometer, AMS, aboard the International Space Station and ground observatories like the Pierre Auger Observatory in Argentina work tirelessly to record cosmic ray data across wide energy ranges and particle types. Their findings enrich our understanding of cosmic ray sources, propagation mechanisms, and the role these particles play on both local and cosmic scales. Thus, cosmic rays are more than mere high-energy particles. They are messengers carrying profound cosmic narratives across time and space. From their elemental makeup to their staggering energies, from the enigmatic acceleration mechanisms to the intricate interplay with galactic magnetic fields, cosmic rays serve as invaluable probes of the energetic processes shaping the universe. Their journey, though invisible to the naked eye, links the phenomena occurring in the most extreme environments to the very air we breathe and the instruments within our scientific grasp. As we continue to explore their spectrum of energies and compositions, we begin to piece together the grand cosmic mosaic they help paint, one where the smallest particles become messengers of some of the universe's largest and most energetic events. Next, we will deepen this exploration by examining the vast spectrum of energies that cosmic rays exhibit, from the humble protons to the rare exotic nuclei, illuminating yet another facet of their fascinating identity. Building on our understanding of what cosmic rays are and their nature as energetic particles originating beyond our planet, we now turn our focus to the diverse and extraordinary spectrum of energies and compositions that define these cosmic travelers. This spectrum is vast, stretching across many orders of magnitude in energy and comprising a fascinating variety of particle types, from the most common and simplest constituents of matter to rare and exotic atomic nuclei. Exploring this spectrum not only reveals the complexity of cosmic rays themselves, but also sheds light on the astrophysical processes capable of producing and accelerating such particles to phenomenal energies. At the heart of cosmic rays' identity lies their energy, a defining characteristic that influences how they interact with matter, magnetic fields, and radiation throughout space. The energies of cosmic rays are measured in electron volts, or EV, a unit reflecting the amount of kinetic energy gained by an electron when accelerated through a 1-volt electric potential. While familiar everyday particles have energies on the order of a few electron volts, cosmic rays encompass energies ranging from a few million electron volts, MeV, up to in excess of 10 to the 20 electron volts, EV, an extraordinary range spanning 14 orders of magnitude. To appreciate the scale, consider that the Large Hadron Collider, LHC, the most powerful particle accelerator on Earth, reaches energies around 10 to the 13 to 10 to the 4 EV, tera electron volts, or TeV energy scales. Yet, cosmic rays routinely surpass this by factors of millions or even billions, making them nature's ultimate particle accelerators and an invaluable resource for high-energy physics research. The cosmic ray energy spectrum features a distinctive pattern when plotted on logarithmic scales. At lower energies, below about 1 GeV, giga electron volt, cosmic rays largely consist of protons and helium nuclei, arriving primarily from the Sun and trapped in the solar wind environment. As energies increase into the range from a few GeV up to about 10^15 GeV, the so-called Ni region, the spectrum steepens, indicating a decline in flux. This is believed to be where galactic sources such as supernova remnants can accelerate particles up to their maximum energies. Beyond the Ni lies the ankle, a subtle flattening of the spectrum around 10 to 18 eV, pointing towards a transition in the dominant origin of cosmic rays from galactic to extragalactic sources. The highest energies, exceeding 10 to 20 and extending beyond 10 to 20, belong to the ultra-high-energy cosmic rays, UHIACORs, which remain subjects of extensive investigation and speculation, given their rareness and mysterious origins. Turning now to the composition of cosmic rays, protons reign supreme, constituting approximately 90% of detected cosmic rays at Earth. Protons are the simplest nuclei, consisting of a single positively charged particle, and their prevalence reflects both the composition of the interstellar medium and the efficiency of acceleration mechanisms acting upon them. Closely following protons are alpha particles, helium nuclei made up of 2 protons and 2 neutrons, composing roughly 9% of cosmic rays. Their relative abundance carries important clues about nucleosynthesis processes in stars and how stellar materials are injected into the interstellar medium. Beyond protons and helium, there exists a fascinating and diverse ensemble of heavier and more exotic nuclei within cosmic rays. These range from lithium, beryllium, and boron, elements primarily produced through spallation reactions, where high-energy cosmic rays collide with interstellar matter, all the way up to iron and beyond. The detection of such nuclei, at varying abundances and isotopic ratios, allows astrophysicists to reconstruct the history of matter, cycling through stellar processes and cosmic ray propagation. Moreover, the presence of rare isotopes and unstable nuclei within cosmic rays provides invaluable information about their journey and time spent traveling through the galaxy. Radioactive isotopes like beryllium-10, for instance, serve as cosmic chronometers that help estimate the confinement time of cosmic rays within our galactic magnetic fields. Intriguingly, cosmic rays also include trace amounts of antimatter particles, such as positrons and antiprotons, which pose further questions about their possible sources. While many positrons likely originate from astrophysical processes, such as pulsars, or the interaction of cosmic rays with interstellar matter, ongoing research probes the tantalizing possibility that some antimatter component may emerge from more exotic phenomena, including dark matter annihilation or decay. The energy spectrum and composition of cosmic rays measured at Earth today are also shaped by the filtering and modulation effects of the solar wind, the stream of charged particles continuously emitted by the Sun, which can attenuate and modulate cosmic ray fluxes at lower energies. This solar modulation varies with the approximately 11-year solar cycle, causing predictable fluctuations in cosmic ray intensity that have been studied extensively through ground-based and spaceborne observatories. The complexity of this energetic spectrum and compositional diversity is mirrored by the wide-ranging experimental approaches used to study cosmic rays. Low to medium-energy cosmic rays can be captured and analyzed directly by detectors aboard spacecraft, while ultra-high-energy cosmic rays, so rare that only a handful strike per square kilometer per century, require massive observational arrays spread over hundreds or thousands of square miles, detecting the secondary particle showers they produce upon impinging Earth's atmosphere. In essence, the cosmic ray spectrum, stretching from simple protons to complex exotic nuclei bearing immense energies, is a rich tapestry woven from the history of matter and energy across the cosmos. It reveals the layered astrophysical processes, from the thermonuclear furnaces of stars, through explosive cataclysms of supernovae, to the energetic environments around black holes and beyond, that collectively act as cosmic accelerators. As we peel back the layers of cosmic ray energies and compositions, we find that each fragment holds a clue. High-energy protons speak of shock waves racing through interstellar space. Helium and heavier nuclei echo the remnants of ancient stellar processes. Rare isotopes and antimatter whisper secrets about cosmic particle production and galactic dynamics. This vast and dynamic spectrum is not static. Rather, it evolves continually under the influence of cosmic phenomena. Understanding it not only enriches our comprehension of astrophysics, but also informs us about the space environment affecting our planet, influencing the Earth's atmosphere, shielding, and even technological systems. In the following section, we will embark deeper into the fascinating debate concerning the origins of these particles, exploring the roles of supernovae, black holes, and other cosmic accelerators that may power the astounding energies we observe. These accelerating forces craft the energetic palette that cosmic rays display, setting the stage for the intricate journey these particles undertake through the universe. As we move further into the fascinating realm of cosmic rays, we encounter one of the most enduring and captivating puzzles in astrophysics: the origins debate. Where do these incredibly energetic particles come from? What cosmic engines impart such vast energies? To address these questions, scientists have explored a variety of celestial phenomena, most notably supernova and black holes, and also probed beyond these to even more exotic possibilities. Understanding cosmic ray origins is not just a matter of identifying their birthplaces. It is an exploration of some of the universe's most violent and energetic processes, shedding light on the forces that govern the cosmos at the largest and smallest scales. Cosmic rays, as we learned, are primarily high-energy protons and atomic nuclei hurtling through space at nearly the speed of light. The challenge lies in explaining how such particles achieve energies ranging from millions to over 100 quintillion electron volts, and from which astrophysical environments they emerge. Early on, the connection between supernova, the explosive deaths of massive stars, and cosmic rays became a leading hypothesis, driven by both observational clues and theoretical considerations. Supernovae are cataclysmic explosions that release enormous amounts of energy, on the order of 10^44 joules, in a matter of seconds, momentarily outshining entire galaxies. They launch shockwaves into the surrounding interstellar medium, creating turbulent, highly magnetized environments ideal for particle acceleration. In fact, these shock fronts are the cradles where charged particles gain energy through repeated interactions, a process known as diffusive shock acceleration. Pioneering works in the mid-20th century proposed that these acceleration mechanisms inside supernova remnants could naturally explain the bulk of galactic cosmic rays observed at Earth up to energies near the knee of the energy spectrum, around 10^42 eV. Observational evidence supports this theory. Supernova remnants emit non-thermal radiation, including radio waves and X-rays, which arise from high-energy electrons gyrating in magnetic fields, a signature of particle acceleration. Gamma-ray observations from space telescopes, such as the Fermi Gamma-ray Space Telescope, have also detected high-energy photons from several supernova remnants, consistent with interactions involving accelerated cosmic ray protons. Despite this evidence, the detailed mechanisms of acceleration, the efficiency with which supernovae convert explosion energy into cosmic ray energy, and the maximum energies attainable remain active research areas. Moving beyond supernovae, the role of black holes as potential cosmic accelerators takes center stage. Black holes, regions of space-time exhibiting gravitational fields so intense that nothing, not even light, can escape, are often surrounded by hot, magnetized plasma and powerful jets of particles that blaze across vast distances. In particular, active galactic nuclei, AGN, powered by supermassive black holes eating matter at the centers of galaxies, are among the most luminous and energetic phenomena known. These AGN jets, traveling near light speed, create enormous shock waves and magnetic turbulence, making them prime candidates for accelerating cosmic rays to ultra-high energies, well beyond the capabilities of supernova remnants. Similarly, stellar mass black holes in binary systems and microquasars can generate smaller-scale but still potent acceleration environments. Gamma-ray bursts, GRBs, fleeting yet extraordinarily energetic explosions thought to originate from collapsing massive stars or neutron-star mergers, have also been proposed as sources of the highest energy cosmic rays. Their brief lifespans and extreme power output provide environments where particles might be accelerated to energies beyond 10^22 V, although confirming this hypothesis remains challenging. Pulsars, rapidly rotating neutron stars with strong magnetic fields, offer another intriguing possibility. The intense electromagnetic fields and winds from these compact objects can act as natural particle accelerators, potentially contributing to the population of cosmic rays, especially electrons and positrons. More exotic sources have been suggested as well, including the decay or annihilation of hypothetical dark matter particles, topological defects formed early in the universe, and other phenomena beyond the standard model of particle physics. While such possibilities currently dwell more in the realm of theoretical speculation, they fuel exciting research as they tie cosmic ray physics to the deepest questions of cosmology and fundamental physics. Despite these compelling ideas, the search for definitive cosmic ray sources remains hindered by a fundamental challenge: the complex paths cosmic rays follow through space. Because these particles are charged, magnetic fields in our galaxy and beyond deflect their trajectories, scrambling the directions from which they arrive at Earth. This magnetic diffusion blurs the connection between observed cosmic rays and their true origin points, making it difficult to map sources unambiguously. To circumvent this obstacle, scientists employ indirect methods. Measuring the energy spectrum and composition of cosmic rays helps identify expected source signatures. For example, if supernova remnants predominantly accelerate heavier nuclei, or if ultra-high energy cosmic rays exhibit a predominance of protons or heavier elements, these clues shape models of source types. Similarly, detecting high-energy photons and neutrinos emitted in tandem with cosmic rays can provide directional information, since these neutral particles travel undeviated by magnetic fields. Groundbreaking neutrino observatories, like the Ice Cube detector in Antarctica, have started to identify high-energy neutrinos coincident with distant astrophysical sources, intersecting with cosmic ray studies and hinting at potential cosmic accelerators. As the debate over cosmic ray origins rages on, one thing is abundantly clear: cosmic rays are intertwined with the most energetic and dynamic processes in the universe. They encompass a cosmic narrative, from the explosive deaths of stars to the fascinating phenomena surrounding black holes and beyond. In this quest, ongoing and future experiments are vital. Enhanced ground arrays, space observatories, and multi-messenger astrophysics, observing cosmic phenomena simultaneously through diverse channels like electromagnetic waves, neutrinos, and gravitational waves, promise to deepen our understanding of cosmic ray sources. By examining these origins, we gain far more than answers about particle acceleration. We unlock insights into stellar evolution, galaxy formation, black hole dynamics, and potentially the very fabric and composition of the universe itself. Our exploration will next turn to the specific mechanisms by which cosmic rays are accelerated to their impressive energies, delving into shock waves sparked by cosmic explosions and other natural accelerators that transform ordinary particles into these extraordinary celestial travelers. In our ongoing exploration of cosmic rays, having glimpsed their diverse origins, ranging from the cataclysmic deaths of stars to the enigmatic activity near black holes, we now turn to the vital question of how these particles are accelerated to the staggering energies that define them. This process of acceleration is fundamental to the identity of cosmic rays, transforming ordinary matter into extraordinary emissaries of high-energy astrophysics. Central to this phenomenon are shock waves and natural particle accelerators operating across the universe, mechanisms that imbue cosmic rays with their immense velocity and energy. Shock waves, in the cosmic context, are akin to the ripples and surges we observe when a supersonic jet breaks the sound barrier or when a ship cuts through water, albeit on incomparably larger and more energetic scales. They are abrupt disturbances in the physical conditions of a medium, such as density, temperature, and pressure, often formed when an object moves faster than the speed of sound through a gas or plasma. In space, shock waves are generated by some of the universe's most violent events: supernova explosions, jets from active galactic nuclei, stellar winds crashing into interstellar gas, and even collision fronts in galaxy clusters. These shock fronts are fertile grounds for accelerating charged particles through a process primarily known as diffusive shock acceleration, or first-order Fermi acceleration, named after physicist Enrico Fermi, who first proposed the concept in the mid-20th century. In essence, charged particles repeatedly cross the shock front, scattering off magnetic irregularities both upstream and downstream. Each crossing statistically boosts the particle's energy, much like a ping-pong ball gaining speed as it bounces repeatedly between moving paddles. Because the energy gain per cycle is proportional to the particle's existing energy, this mechanism is highly efficient in producing particles with energies spanning many orders of magnitude. In supernova remnants, where a massive star's outer layers explode outward at thousands of kilometers per second, shock waves plow through the interstellar medium. These shocks compress and amplify magnetic fields, creating turbulent regions where particles can be confined and accelerated. Observations of synchrotron radiation emitted by electrons spiraling around magnetic field lines provide direct evidence of ongoing particle acceleration in these sites. The spectral signatures captured by radio, X-ray, and gamma-ray telescopes confirm that shock waves accelerate not only electrons, but also protons and heavier nuclei, lending strong support to the idea that supernova remnants are the dominant source of galactic cosmic rays up to energies of about 10^15 9. Beyond supernovae, jets emanating from active galactic nuclei, supermassive black holes at the centers of galaxies, produce colossal shocks as they blast plasma at near-light speeds into extragalactic space. These environments, colossal in scale and energy, serve as powerful accelerators capable of energizing particles to ultra-high energies exceeding 10^19 eV. Here, the same principles of shock acceleration operate, augmented by shear flows, magnetic reconnection, and turbulence in highly magnetized plasmas. Another particle acceleration mechanism closely related to shocks is magnetic reconnection, a process where opposing magnetic field lines break and reconnect, releasing prodigious energy. This occurs in many astrophysical environments, including solar flares, pulsar magnetospheres, and the vicinity of black holes. While not shock acceleration per se, magnetic reconnection can energize particles rapidly, complementing the acceleration mechanisms shaping cosmic ray populations. The complexity of these acceleration processes extends further when considering the interactions of cosmic rays with their environment. Once accelerated, cosmic rays continue to experience scattering off magnetic turbulence, gaining or losing energy through additional interactions. These processes play a significant role in determining both the energy spectrum and spatial distribution of cosmic rays observed near Earth. Importantly, the efficiency of shock acceleration depends heavily on various parameters: the velocity of shock fronts, the strength and geometry of magnetic fields, and the density of the surrounding medium. Theoretical models and computer simulations have become indispensable tools in unraveling how these factors influence particle acceleration. Advances in magnetohydrodynamics, MHD simulations provide detailed insights into shock structure, particle injection, and escape, enabling researchers to refine predictions about cosmic ray energies and fluxes. Laboratory plasma experiments and observations of the solar wind also contribute to our understanding by providing natural testbeds of shock and acceleration physics at much smaller scales. For example, Earth's bow shock formed where the solar wind encounters the planet's magnetic field offers a nearby laboratory, where in situ spacecraft measurements have revealed the microphysics of particle acceleration and turbulence. Another fascinating concept related to cosmic ray acceleration is the potential contribution of so-called re-acceleration processes, whereby cosmic rays that have previously gained energy may encounter subsequent shocks or turbulent regions, receiving additional boosts. This cumulative acceleration helps explain the broad, continuous nature of the cosmic ray energy spectrum. The profound implications of shock acceleration extend beyond the mere production of energetic particles. Cosmic rays themselves can influence the medium they inhabit by exerting pressure and instigating waves and instabilities in magnetic fields. This feedback shapes the evolution of supernova remnants, galactic winds, and even the formation of cosmic structures on large scales. As our understanding deepens, researchers explore a variety of model refinements and hybrid acceleration mechanisms to explain observed phenomena. For instance, acceleration at relativistic shocks, where shocks move close to the speed of light, introduces complexities in particle distribution and interaction rates, critical for interpreting ultra-high-energy cosmic ray data. In sum, the breathtaking energies embodied by cosmic rays are the result of cosmic accelerators operating across a spectrum of astrophysical environments, with shock waves playing a central role. These natural particle accelerators convert kinetic and magnetic energy from cosmic explosions and jets into the kinetic energy of high-velocity charged particles. The efficiency and universality of these processes underscore the dynamic, ever-changing character of the universe. Having gained insight into how cosmic rays acquire their formidable energies, our journey will next explore the vast distances these energetic voyagers traverse. We will delve into their epic journey through interstellar space, examining how magnetic fields, gas, and dust shape their trajectories and interactions before they finally reach our planet. Their passage through the cosmic void is as compelling as their origin and acceleration, revealing more about the universe's hidden structure and the subtle forces guiding these charged messengers. Having understood how cosmic rays acquire their immense energies through powerful cosmic accelerators, such as shock waves in supernova remnants and energetic jets near black holes, we turn now to an equally profound question. Where in the vast cosmic landscape do these energetic particles originate? The answer lies in a dynamic interplay between sources within our own Milky Way galaxy and those from the far reaches of extragalactic space. The cosmic rays reaching Earth today are, therefore, a complex blend of voyagers from the edge, traversing space across multiple scales and boundaries. Cosmic rays observed on Earth originate from two principal source populations: galactic and extragalactic. Galactic cosmic rays are particles accelerated within our Milky Way, whereas extragalactic cosmic rays come from sources beyond our galactic borders, possibly spanning billions of light-years. Distinguishing between these populations is an ongoing endeavor and crucial for a comprehensive understanding of cosmic ray physics. Within our galaxy, supernova remnants have long been considered the primary factories of galactic cosmic rays. The shock waves generated by these exploding stars propagate through the interstellar medium, imparting energies to protons and heavier nuclei. The Milky Way is also home to other potential accelerators such as pulsars and binary star systems hosting black holes and neutron stars, which can power relativistic jets and magnetized winds, contributing further to the cosmic ray population. Galactic cosmic rays generally make up the majority of particles, with energies up to around 10^15 to 10^16 electron volts, at eV. Their energies and composition reflect the local astrophysical environments prevalent within our galaxy. These particles are confined to the Milky Way's magnetic fields for millions of years, undergoing diffusion and scattering before gradually escaping into intergalactic space. This confinement and their interactions with interstellar gas influence their energy spectrum and chemical signatures observed near Earth. However, cosmic rays do not stop at the galactic boundary. At energies exceeding approximately 10 eV, the region known as the ankle in the cosmic ray energy spectrum, evidence strongly suggests that particles start to originate from extragalactic sources. These ultra-high energy cosmic rays, UHECRs, possess energies that are far beyond what known galactic sources can achieve, implying the need for extraordinarily powerful accelerators beyond the Milky Way. Active galactic nuclei, AGN, the accreting supermassive black holes at the cores of distant galaxies, are compelling candidates for extragalactic cosmic ray sources. Their jets can extend for thousands of light years and host extreme magnetic fields and shock waves capable of accelerating particles to the upper echelon of the cosmic ray energy spectrum. Similarly, gamma-ray bursts, GRBs, among the most energetic events observed in the universe, might contribute to ultra-high-energy cosmic rays, though their transient nature poses detection challenges. One of the key puzzles regarding extragalactic cosmic rays involves their interaction with the cosmic microwave background, CMB, the pervasive relic radiation from the Big Bang. When ultra-high-energy cosmic rays propagate through space, they can interact with CMB photons, losing energy through processes such as pion production in a phenomenon known as the Greisen-Zatsepin-Kuzmin (GZK) effect. This theoretical prediction implies a cutoff in the cosmic ray spectrum at the highest energies detected on Earth, adding complexity to the interpretation of their origins. Distinguishing cosmic rays of galactic origin from those of extragalactic provenance is challenging due to their charged nature. Magnetic fields in both the Milky Way and intergalactic space bend their trajectories, erasing obvious directional signatures. Nevertheless, research seeks subtle anisotropies, small variations in the arrival directions of cosmic rays, to glean clues about their sources. Large-scale observatories, such as the Pierre Auger Observatory and the Telescope Array, employ vast detector networks covering hundreds of square kilometers to monitor these directional patterns, contributing valuable data toward this goal. Additionally, differences in cosmic ray composition offer important clues. Galactic cosmic rays tend to show a heavier elemental composition relative to extragalactic cosmic rays, which are often more proton-rich at the highest energies. These compositional differences reflect the nature of acceleration sites and propagation effects and help refine models of cosmic ray origins. Complementing charged cosmic ray studies, multi-messenger astronomy explores neutral particles, especially neutrinos and photons, that can travel in straight lines from their sources. Detecting high-energy neutrinos, nearly massless and unaffected by electromagnetic forces, provides a unique window into energetic extragalactic accelerators and cosmic ray origins. Notably, observatories like IceCube have begun detecting astrophysical neutrinos coincident with distant AGN flares, hinting at connections between these particles and ultra-high-energy cosmic rays. Furthermore, cosmic rays of extragalactic origin provide a lens into the large-scale structure of the universe. Their paths encode information about magnetic fields in voids and filaments that thread between galaxy clusters, offering precious insights into cosmic magnetism that remains poorly understood. While cosmic rays are often thought of as distant travelers, the subtle balance between their galactic origins and extragalactic journeys emphasizes a complex and interconnected universe. These particles trace pathways from the explosive environments within our cosmic backyard to the vast and sometimes mysterious accelerators scattered throughout the observable universe. As we deepen our understanding of cosmic rays from both galactic and extragalactic sources, attention turns to the incredible voyage they embark upon through interstellar space. The next chapter will chart the intricate voyage cosmic rays undertake across the void, navigating magnetic fields, interacting with gas and dust, and surviving the vast expanses of space before eventually reaching Earth's neighborhood. This journey through the void reveals as much about the universe's structure and forces as it does about the particles themselves, continuing the story of these extraordinary celestial voyagers. Having explored the origins of cosmic rays both within our galaxy and beyond, as well as the powerful accelerators that endow these particles with incredible energies, we now delve into the epic journey these cosmic voyagers undertake through interstellar space. This vast expanse between stars, seemingly empty at first glance, is in fact a dynamic and complex environment that shapes the trajectories, energies, and even the fates of cosmic rays before they finally reach our planetary neighborhood. Interstellar space, the cosmic void between stars within our Milky Way, is filled with a tenuous mixture of gas, dust, magnetic fields, and cosmic rays themselves. Despite its low density compared to any terrestrial vacuum, this medium is far from empty. It forms a vast and intricate tapestry of plasma and magnetic fields, collectively referred to as the interstellar medium, ISM. Cosmic rays traversing this environment must navigate turbulent magnetic landscapes and interactions with interstellar particles, influencing their propagation and energy spectra observed at Earth. Due to their electric charge, cosmic rays do not travel in straight lines through space. Instead, their paths twist and bend under the influence of magnetic fields threading the ISM. These magnetic fields, although weak, on the order of a few microgauss, extend over enormous regions, guiding and confining cosmic rays within the galaxy for prolonged periods. Instead of a direct beam pointing back to their sources, cosmic rays perform a complex random walk, scattering off magnetic irregularities and undergoing diffusion. This wandering journey obscures their origins, but also prolongs their lifetimes within the galaxy. Propagation models of cosmic rays simulate this diffusive behavior, characterizing how particles of different energies and charges scatter and move through the ISM. The effectiveness of this scattering depends strongly on particle properties and magnetic field structures. Generally, lower-energy cosmic rays, more easily deflected by magnetic turbulence, remain confined within the galaxy for millions to tens of millions of years before escaping into intergalactic space. Higher-energy particles, with their greater rigidity, traverse the ISM more directly and escape more readily. While propagation is dominated by magnetic effects, cosmic rays also interact with the sparse gas and dust in interstellar space. Collisions between cosmic rays and interstellar nuclei can strip nucleons, create secondary particles, and instigate nuclear spallation processes. These interactions enrich the cosmic ray composition with lighter elements such as lithium, beryllium, and boron, which are otherwise scarcely produced in stars. Measuring these secondary cosmic rays provides critical information about the amount of material cosmic rays have traversed and the timescales of their journey. Moreover, cosmic rays influence the ISM itself. Their presence contributes a significant pressure component alongside thermal gas and magnetic fields, affecting the dynamics and stability of interstellar clouds. Cosmic ray-driven turbulent motions can initiate or suppress star formation, regulate gas heating, and mediate processes within molecular clouds where new stars are born. Hence, their journey through the void simultaneously shapes and is shaped by the galactic environment. One might also consider the cosmic rays' passage through larger-scale structures like superbubbles, vast cavities carved by multiple supernova explosions and stellar winds. Superbubbles provide extended regions of hot, low-density plasma and potentially enhanced magnetic turbulence, influencing cosmic ray confinement and reacceleration. These structures act as both corridors and traps in the galactic cosmic ray odyssey. As cosmic rays approach the Sun's neighborhood, they encounter the heliosphere, the bubble carved out by the solar wind and solar magnetic fields into the surrounding ISM. The heliosphere serves as a boundary that modulates low-energy cosmic rays reaching the inner solar system. The solar wind's magnetic turbulence and plasma flows deflect and decelerate particles, leading to the well-documented solar modulation effect, where cosmic ray intensities vary in sync with the approximately 11-year solar cycle. This modulation complicates precision measurements of cosmic rays near Earth, but also offers a valuable probe of solar and heliospheric physics. Spacecraft such as Voyager 1 and 2, which have journeyed beyond the heliopause, provide direct measurements of cosmic ray fluxes in interstellar space, enhancing our understanding of particle transport across this boundary. In addition to confined propagation, cosmic rays may experience reacceleration during their interstellar journey, gaining additional boosts in energy by encountering successive shock waves, turbulent fields, or magnetic reconnection sites within the ISM. This process can help explain the continuous and extended energy spectrum observed, demonstrating that cosmic ray energies are dynamic, evolving throughout their voyage. Furthermore, the journey through the void is not without peril. Ultra-high-energy cosmic rays can collide with photons of the cosmic microwave background, losing energy through interactions that set theoretical limits on their maximum reach. Such energy losses, collectively described by the GZK cutoff, shape the highest energy portion of the cosmic ray spectrum and confine their viable sources to relatively nearby extragalactic distances. In totality, the cosmic ray voyage across interstellar space is a saga of confinement, interactions, modulation, and transformation. The particles we detect near Earth have been molded by magnetic fields, gas densities, shock waves, and complex physical processes, stretching across tens of thousands of light years and millions of years of travel time. By understanding these propagation effects, scientists can backtrack cosmic ray data to create models of source populations and galactic environments, slowly piecing together the origins and roles these particles play in the cosmic ecosystem. Next, we will examine how Earth's atmosphere itself becomes an extension of this cosmic puzzle, acting as a natural detector where cosmic rays collide with atmospheric nuclei, generating spectacular particle cascades known as air showers. Studying these cascades unlocks insights not just into cosmic rays' nature and origins, but also into the invisible influences shaping our planet's atmospheric and space environments. As cosmic rays embark on their long voyages from distant cosmic accelerators, the moment of their grand arrival at Earth marks a fascinating interaction that transforms the invisible messengers into spectacular cascades of subatomic particles. The Earth's atmosphere itself acts as an enormous natural detector, revealing the presence and properties of cosmic rays through the complex phenomena known as extensive air showers. Understanding these air showers is pivotal, for within them lies the key to unlocking cosmic rays' secrets, bridging the gap between the distant cosmos and terrestrial instruments capable of capturing their fleeting imprints. When a high-energy cosmic ray particle, typically a proton or an atomic nucleus traveling near the speed of light, enters the Earth's atmosphere, it collides with a nucleus of atmospheric atoms, such as nitrogen or oxygen, high above us, often at altitudes exceeding 15 kilometers. This initial collision is violent, shattering atomic nuclei and producing a shower of secondary particles. These secondary particles, in turn, propagate downwards and interact further, triggering a cascading chain reaction that exponentially multiplies the number of particles traveling through the atmosphere. This is the essence of an air shower. Air showers can be envisioned as giant, cone-shaped avalanches of particles sweeping through the atmosphere at nearly the speed of light. They produce a rich mixture of particle types: electrons, positrons, muons, photons, and other subatomic constituents. This cascade continues until the energy of the particles is depleted through interactions and ionization losses, causing the shower to eventually dissipate as particles reach the Earth's surface or decay mid-air. The development and structure of air showers depend critically on the energy and composition of the primary cosmic ray particle, as well as the altitude and properties of the atmosphere it traverses. Higher energy primaries initiate larger and more penetrating showers, with millions or even billions of secondary particles reaching the ground in rare ultra-high energy events. Conversely, lower energy particles produce more modest cascades, detectable primarily through indirect effects, like atmospheric ionization. One key feature of air showers is the production of muons, heavier cousins of electrons. These muons are produced deep in the shower development, and due to their relatively long lifetimes and penetrating power, can reach Earth's surface or underground detectors. Their abundance and arrival times carry essential information aiding in the reconstruction of the original cosmic ray properties. Another remarkable consequence of air showers is the generation of faint flashes of light, known as Cherenkov radiation and fluorescence. When charged secondary particles travel through the atmosphere faster than the speed of light in air, which is slightly less than in a vacuum, they emit Cherenkov light, a bluish glow similar to the sonic boom of supersonic aircraft, but in electromagnetic form. Additionally, when atmospheric nitrogen molecules are excited by passing particles and subsequently relax, they emit fluorescent ultraviolet light. Sophisticated detectors on the ground can capture these fleeting light signals, allowing researchers to track the development and trajectory of the air shower across the sky. Historical recognition of the atmosphere as a cosmic ray detector dates back nearly a century. Early observations noticed bursts of coincident particle detections at ground level during cosmic ray events, hinting at cascades rather than isolated particle strikes. Later advances, including cloud chambers, Cherenkov telescopes, and scintillation detectors, enabled scientists to record and analyze the complex patterns of extensive air showers with increasing precision. The scale of these air showers is staggering. Ultra-high energy cosmic rays can produce showers that spread over several square kilometers upon reaching Earth's surface. This spatial extent led to the establishment of large-scale observatories, such as the Pierre Auger Observatory in Argentina and the Telescope Array in Utah, USA. These facilities deploy thousands of detectors over immense areas to measure the density, timing, and composition of secondary particles, piecing together the original cosmic rays' identity and energy. Air shower detection techniques are broadly divided into ground-based particle detectors and optical telescopes observing atmospheric light emissions. Ground arrays, utilizing water Cherenkov detectors or scintillators, measure secondary particles directly, while fluorescence and Cherenkov telescopes track the atmospheric light produced by showers, providing complementary information. Combining data from these techniques allows scientists to reconstruct the direction, energy, and composition of cosmic rays with remarkable accuracy. They also enable investigations into anisotropies, variations in arrival directions that offer clues about cosmic ray origins and the magnetic fields they traverse. Beyond their scientific value, extensive air showers embody a natural particle physics laboratory. The interactions of cosmic ray primaries at energies often surpassing those achievable by human-built accelerators provide insight into fundamental particle physics, testing models of high-energy interactions and advancing our understanding of matter under extreme conditions. Moreover, air showers indirectly influence Earth's environment. The ionization produced affects atmospheric chemistry, playing a role in cloud formation and electrical properties of the atmosphere, topics that connect cosmic rays to Earth's weather and climate systems. In this way, Earth's atmosphere is far more than a passive shield. It is an intricate, dynamic detector that translates the high-energy universe into signals we can observe and study. It is the stage where cosmic phenomena from across the universe leave their fingerprints, accessible to human curiosity and ingenuity. Our understanding of air showers thus forms a crucial link, connecting the distant astrophysical origins of cosmic rays to the technologies and observatories we develop to decode their messages. In the upcoming sections, we will explore the pioneering efforts that leveraged early balloon flights and cloud chambers to uncover cosmic rays mysteries and examine modern detection techniques that continue to push the boundaries of this exciting field. Stepping back to the early 20th century, the journey to understand cosmic rays took shape through a series of pioneering observations that melded daring exploration with groundbreaking technological innovation. The era was marked by instrumentation that, while rudimentary by today's standards, laid the foundation for all subsequent cosmic ray research. Of particular importance were high-altitude balloon flights and the advent of the cloud chamber, tools that transformed the invisible cosmic radiation into visible particle tracks and brought the mysteries of these energetic travelers into sharper scientific focus. Before these innovations, the presence of ionizing radiation was detected only indirectly through unexpected discharges in electroscopes or atmospheric ionization measurements that hinted at some penetrating radiation. The groundbreaking work of Victor Hess, who famously ascended in balloons to heights beyond 5,000 meters, confirmed that the ionization level increased with altitude, implicating an extraterrestrial origin for these rays. His courageous flights provided the first direct evidence that the radiation intensified as one moved away from the Earth's surface, an observation that turned the scientific world's attention outward into the cosmos. Balloon flights quickly became the vessel of choice for cosmic ray explorations, offering access to the upper atmosphere where the intensity and behavior of cosmic rays could be studied with less interference. These flights carried electroscopes and later more sophisticated instruments to great heights, mapping variations in cosmic ray intensity with altitude, latitude, and solar activity. These early missions revealed that cosmic rays were not a monolithic phenomenon, but varied with geomagnetic latitude due to the shielding effect of Earth's magnetic field, and with time as influenced by solar cycles. Parallel to these aerial endeavors, the invention of the cloud chamber revolutionized cosmic ray research by allowing direct visualization of particle interactions. Developed in the early 20th century by Charles Wilson, the cloud chamber operates on the principle of supersaturation, enabling vapor to condense into tiny droplets along the trails of charged particles. In doing so, it reveals the otherwise invisible tracks of atomic and subatomic particles, offering tangible evidence of cosmic ray components hitting the chamber. The first successful images of cosmic ray tracks in cloud chambers depicted intricate spirals and linear trails, proving beyond doubt the particle nature of cosmic rays. These observations provided insights into the types of particles involved, such as electrons, protons, and heavier nuclei, and their energy and charge properties. The cloud chamber became an indispensable laboratory tool, enabling physicists to identify previously unknown particles and phenomena. It played a crucial role in the discovery of the positron in 1932 by Carl Anderson, an antiparticle to the electron, identified within cosmic ray showers and marking a major milestone in particle physics. Complementing cloud chambers were photographic emulsions, and later bubble chambers, but initial balloon flights with cloud chambers positioned at high altitudes pushed the technological envelope even further. They allowed for particle detection closer to the cosmic ray sources before the atmospheric shower development could complicate measurements. Remarkably, these early endeavors did not only enhance scientific understanding, but also inspired novel methods and instruments. For example, cloud chambers paired with magnetic fields allowed researchers to measure particle momentum and charge by observing curvature in particle trajectories, while time-of-flight measurements and scintillators were gradually integrated to expand detection capabilities. Despite their simplicity compared to modern detectors, these pioneering observations provided the essential empirical underpinning for cosmic ray science. They confirmed the charged nature of cosmic rays, mapped their intensity distributions, and identified fundamental particle components that could be linked to cosmic and terrestrial processes. Moreover, the results stimulated cross-disciplinary advances, bridging astrophysics and particle physics and ushering in the era of high-energy physics. These early observational campaigns faced enormous challenges, from technical limitations and instrumentation weight constraints on balloons to the vagaries of weather, limited data transmission, and the inherently stochastic nature of cosmic radiation. Yet, the resolve and ingenuity of early 20th century scientists overcame these hurdles, laying out the principles guiding modern cosmic ray observatories and particle detectors. As we move forward into the development of detection technologies of the modern era, these initial steps serve as a reminder of how foundational exploration and innovation converge to transform mystery into knowledge. The progression from rudimentary electroscopes and valiant balloon flights to today's vast ground arrays and sophisticated space-based instruments reflects a century-long journey propelled by human curiosity and persistence, ever reaching to comprehend the cosmic rays that sculpt our universe. As cosmic ray research evolved through the pioneering observations of early balloon flights and the ingenious use of cloud chambers, the quest to decode the arrival of these high-energy particles entered a new era, one marked by rapid technological advancement and growing scientific sophistication. Modern cosmic ray detection technologies have transformed our ability to measure, analyze, and interpret these elusive messengers, offering unprecedented insights into their composition, energy, and origins. This chapter chronicles the innovative instruments, observatories, and methodologies that define the detection of cosmic rays today, highlighting how they enable researchers to untangle the intricate cosmic signals that continuously impinge on our planet. One of the cornerstones of contemporary cosmic ray detection is the array of ground-based particle detector networks scattered across vast expanses of Earth's surface. These arrays employ thousands of individual detectors, such as scintillators, water Cherenkov tanks, and resistive plate chambers, each designed to sample the secondary particles arriving from cosmic ray-induced air showers. The detectors measure particle densities, arrival times, and energy depositions to reconstruct the direction, energy, and identity of the primary cosmic ray particle. A flagship example is the Pierre Auger Observatory in Argentina, encompassing over 3,000 square kilometers dotted with more than 1,600 water Cherenkov detectors. When muons and electrons from an air shower pass through these water tanks, they emit subtle flashes of Cherenkov light, which photomultiplier tubes capture. Synchronizing signals from an entire detector array using GPS timing enables precise reconstruction of shower fronts, facilitating determinations of the cosmic ray's energy and incident angle with remarkable accuracy. Complementing ground arrays are fluorescence detector telescopes, strategically situated around the perimeter of large observatories. These instruments observe the faint, ultraviolet light emitted by nitrogen molecules excited by the passage of air shower particles. By tracking the temporal and spatial development of the fluorescence signals, scientists construct three-dimensional profiles of air showers, revealing critical parameters about the primary particle. The Pierre Auger Observatory, the telescope array in Utah, and the Fly's Eye experiment pioneered and refined these techniques. Space-based observatories have further revolutionized cosmic ray detection by circumventing limitations imposed by Earth's atmosphere and enabling global coverage. The Alpha Magnetic Spectrometer, AMS-02, installed aboard the International Space Station, exemplifies this leap. AMS employs a powerful superconducting magnet and a suite of particle detectors, including a transition radiation detector, time-of-flight systems, and silicon tracker arrays, to identify and measure the charge, mass, and energy of cosmic rays directly, often before they begin air shower development. This direct detection allows for exquisite determination of elemental and isotopic compositions, enriching our understanding of cosmic ray sources and propagation. Similarly, the Calorimetric Electron Telescope, CALET, and the Dark Matter Particle Explorer, DAMP, orbiting satellites equipped with calorimeters and particle trackers, measure cosmic ray spectra up to extremely high energies, probing for signatures of exotic physics and probing the subtle shoulders of the cosmic ray energy distribution. Radio detection has emerged as a compelling contemporary method, exploiting the radio frequency emissions produced by particle showers in the atmosphere. When secondary electrons and positrons in an air shower are deflected by Earth's magnetic field, they emit coherent radio pulses, a phenomenon known as geomagnetic emission. Experiments like LOFAR, Low Frequency Array, and ERA, Auger Engineering Radio Array, use dense grids of radio antennas to detect and characterize these signals, offering complementary data to traditional particle detectors and fluorescence telescopes. This technique provides a high duty cycle and large effective detection area at relatively low cost. Innovative detection methods also include Cherenkov telescopes that detect the Cherenkov light emitted by high-energy particles in the atmosphere, such as the High Energy Stereoscopic System, HESS, and the upcoming Cherenkov Telescope Array, CTA. Although primarily designed for gamma-ray astronomy, these instruments contribute insights into cosmic ray physics by studying secondary gamma photons generated in cosmic ray interactions. At lower energies, underground laboratories utilizing deep rock shielding employ massive arrays of scintillation detectors and tracking chambers to detect muons and neutrinos generated by cosmic ray interactions or penetrating cosmic rays themselves. Facilities such as the Super Kamiokande in Japan and the Ice Cube Neutrino Observatory in Antarctica push the boundaries of cosmic ray studies into neutrino and indirect detection regimes, coupling cosmic rays with multi-messenger astrophysics. Key to all these modern detectors is the integration of sophisticated data acquisition systems and advanced computational frameworks. Real-time data processing, machine learning algorithms for pattern recognition, and large-scale simulations of particle interactions enrich observational datasets, yielding nuanced interpretations. These approaches allow scientists to refine cosmic ray energy spectra, investigate composition on elemental and isotopic scales, and search for anisotropies hinting at source directions. Calibration and cross-validation between different detection modalities mitigate systematic uncertainties, while global collaboration networks enhance temporal and spatial coverage of cosmic ray events. Projects like the Global Muon Detector Network, GMDN, track cosmic ray modulation related to space weather, illustrating practical applications intertwined with fundamental research. Modern detection technologies have thus matured into comprehensive systems, synergistically combining ground, atmospheric, and space-based platforms to capture the multifaceted nature of cosmic rays. They empower researchers to tackle some of the grandest questions in astrophysics, where cosmic rays come from, how they propagate, and what roles they play in cosmic evolution. As we continue this exploration, the following chapter will turn to the challenges cosmic rays pose to human endeavors in space, exploring the potential dangers they represent to astronauts and spacecraft, and the measures designed to mitigate these threats. Understanding cosmic rays not only satisfies cosmic curiosity, but also holds practical implications for humanity's future in space exploration. As we have journeyed through the nature, origins, and detection of cosmic rays, it becomes clear that these energetic particles, while illuminating the cosmos, pose a significant and pressing challenge for humanity's ventures beyond Earth. The interaction between cosmic rays and human spaceflight constitutes a critical area of study that intertwines astrophysics, space medicine, and engineering. Unlike the protective cocoon the Earth's atmosphere and magnetic field provide to life on the surface, spacefaring humans and their spacecraft stand exposed to cosmic radiation, including the continuous bombardment of cosmic rays, some carrying energies beyond human-made accelerator capabilities. In this segment, we explore the dangers cosmic rays present to astronauts and equipment, the biological consequences, ongoing research, and mitigation strategies vital for the future of human space exploration. Outside the blanket of the Earth's atmosphere and magnetosphere, cosmic rays become a formidable source of ionizing radiation. Composed mostly of high-energy protons and fully ionized nuclei, cosmic rays possess strong penetrative power, allowing them to pass through spacecraft hulls, human tissue, and electronic components. While Earth-based life is well shielded, astronauts aboard the International Space Station, ISS, and, prospectively, manned missions to the Moon, Mars, and beyond confront radiation doses that far exceed terrestrial levels. The biological implications of cosmic ray exposure are severe and multifaceted. High-energy cosmic rays can ionize molecules within human cells, damaging DNA and other cellular structures. This damage increases the risk of acute effects such as radiation sickness during extreme solar particle events and, more insidiously, long-term health consequences, including increased cancer risk, degenerative diseases, cataracts, and central nervous system impairments. Cosmic ray-induced cellular mutations also have the potential to affect reproduction and induce hereditary effects, raising critical concerns for long-duration missions. Unlike terrestrial radiation exposures, cosmic rays include highly charged heavy ions, known as high charge and energy, HZE particles, which create dense tracks of ionization and complex DNA damage. The unique nature of HZE particles complicates biological damage assessment and necessitates specialized research, as the traditional models for radiation risk derived from gamma and X-ray exposures may underestimate the risks of cosmic rays. Electronics and spacecraft materials similarly face substantial challenges. Cosmic rays can induce single-event upsets, SEUs, and damage in microelectronics, leading to errors in spacecraft instruments and potential system failures. Shielding measures must balance weight constraints with protective efficacy, making material science and engineering innovative priorities in spacecraft design. Understanding the cosmic ray environment in real time is crucial for mission safety. The ISS is equipped with instruments such as the Radiation Assessment Detector, HRAD, to monitor and characterize particle fluxes continually. Solar activity plays a dual role. During periods of high solar activity, increased solar wind and magnetic field turbulence can partially shield interplanetary space from galactic cosmic rays, effectively lowering exposure. However, solar particle events emit intense bursts of lower-energy protons that can deliver acute radiation doses, posing immediate risk. Future deep space missions, particularly to Mars and beyond, will face more severe and protracted cosmic ray exposure. Unlike the relatively protected low Earth orbit, these missions lack the Earth's magnetic shield and atmospheric protection. The transit duration, combined with the cumulative radiation dose, demands robust countermeasures and mission planning to mitigate health risks. Mitigation strategies involve a host of approaches. Active shielding concepts employing magnetic or electric fields to deflect charged particles, passive shielding through spacecraft hull materials and specialized polymers, and biological countermeasures including pharmaceutical radioprotectors and antioxidants. Additionally, mission architecture planning, such as timing missions to solar maximum phases, employing storm shelters within spacecraft, and limiting extravehicular activities during heightened radiation periods, forms part of an integrated defense strategy. Ground-based research facilities replicate cosmic ray exposures using particle accelerators to understand biological effects and test shielding technologies. This vital research informs astronaut health protocols and feeds into risk models used by space agencies. Psychological effects, although indirectly related, are exacerbated by the potential health risks and the isolation of space missions. Comprehensive astronaut training and psychological support systems are integral to managing the complex challenges posed by cosmic rays. In parallel, advancements in real-time space weather forecasting aim to provide early warnings of solar particle events, allowing mission controllers and astronauts to take protective actions. This proactive approach is essential given the unpredictability and potential lethality of solar radiation storms. The International Space Station serves as an invaluable testbed for understanding chronic cosmic ray exposure and evaluating protective measures. Its continuous human presence and sophisticated monitoring instruments provide ongoing data critical to planning longer, deeper missions. As humanity prepares for the next frontier of exploration, establishing lunar bases, sending crewed missions to Mars, or journeying to asteroids, the imperative to understand and mitigate cosmic ray hazards grows more urgent. This challenge spans disciplines, uniting astrophysics, biology, medicine, materials science, and engineering in pursuit of safe, sustainable human presence beyond Earth. Ultimately, cosmic rays are both a bridge and a barrier. They connect us to the high-energy universe while posing risks that test our ingenuity and resolve. By decoding their behavior and effects in spaceflight, we not only protect explorers venturing into the cosmic sea, but also deepen our understanding of cosmic phenomena, highlighting the intrinsic link between human endeavors and the universe's energetic fabric. With these critical issues in mind, our exploration will next reveal the subtle but profound role cosmic rays play beyond direct physical impacts, as invisible architects influencing the chemistry of the cosmos itself. Their interactions with matter and radiation initiate processes that help shape the very universe we seek to explore. In the vastness of space, cosmic rays are not simply speeding particles that traverse the cosmic web. They are subtle, yet powerful architects that influence the very chemistry of the universe. Beyond their physical presence as high-energy cosmic projectiles, cosmic rays initiate transformations in matter and radiation fields that shape the composition, ionization, and evolution of diverse astrophysical environments, from diffuse interstellar clouds to the dense nurseries of star formation. The intricate interplay between cosmic rays and the chemistry of the cosmos is a profound narrative, revealing how these invisible messengers mold the very fabric of space and matter. One of the most compelling aspects of cosmic rays' chemical influence is their role as ionizing agents within interstellar clouds. Despite the sparse density of these clouds, vast accumulations of gas and dust occupying the spaces between stars, cosmic rays penetrate deep into their interiors, ionizing atoms and molecules. This ionization process produces charged particles such as ions, and free electrons, which are essential catalysts for chemical reactions that would otherwise proceed sluggishly or be entirely suppressed. Unlike ultraviolet photons and X-rays, which are absorbed in the cloud's outer layers, cosmic rays can reach regions shielded from ordinary radiation, seeding the cores of molecular clouds with ionization and driving complex chemistry. The ionization initiated by cosmic rays fosters a rich astrochemical environment. For example, when cosmic rays ionize molecular hydrogen, H2, a cascade of ion-molecule reactions begins, leading to the formation of pivotal molecular ions such as H3+. This ion is a fundamental building block for the creation of more complex molecules, laying the foundation for the diverse organic chemistry observed in interstellar space. Observations of H3+ in molecular clouds provide direct evidence of cosmic ray ionization rates and hint at the physical conditions within dense regions where stars and planets are born. Furthermore, cosmic ray-induced ionization triggers gas phase pathways, leading to the synthesis of a variety of molecules, including water, H2O, carbon monoxide, CaCO, ammonia, NH3, and an extensive array of organic molecules, some of which are precursors to prebiotic chemistry. This chemistry sets the stage for subsequent molecular evolution, influencing the composition of protoplanetary disks and the initial chemical inventory of forming planetary systems. Beyond gas phase chemistry, cosmic rays influence the interaction of dust grains with their environment. Interstellar dust, microscopic solid particles composed of silicates, carbon compounds, and ices, plays a key role in molecular hydrogen formation and provides surfaces for chemical reactions. Cosmic rays facilitate processes such as the desorption of molecules from dust grain surfaces, allowing chemical species to return to the gas phase and participate in further reactions. Additionally, cosmic rays can alter the physical structure and composition of dust grains through sputtering and implantation, modifying grain surfaces and influencing their optical and catalytic properties. Another notable consequence of cosmic ray chemistry involves the heating of interstellar gas. The energy deposited by ionization and secondary electrons from cosmic ray interactions raises the gas temperature by several degrees Kelvin, influencing cloud stability and the balance between gravitational collapse and pressure support. This heating effect modulates conditions for star formation, affecting cloud fragmentation and the initial mass function of stars. On larger scales, cosmic rays contribute to the ionization and chemical processes in circumgalactic and intergalactic mediums. These vast reservoirs of tenuous gas envelop galaxies and fill cosmic filaments, playing vital roles in galaxy formation and evolution. Here, cosmic rays influence magnetic field generation, gas cooling, and the ionization state that determines radiative processes, thereby sculpting galaxy environments. Cosmic rays also impact planetary atmospheres and surface chemistry. For example, cosmic ray ionization in planetary ionospheres affects electrical conductivity, chemical composition, and the formation of aerosols, which in turn influence climate and habitability. On Earth, cosmic ray-induced chemistry contributes to the production of isotopes like carbon-14 and beryllium-10, which serve as chronological markers in geology and climatology. At a more fundamental level, cosmic rays have been implicated in the synthesis of rare isotopes through spallation reactions, where cosmic rays fragment atomic nuclei of interstellar material. This spallation contributes to the presence of light elements such as lithium, beryllium, and boron, whose abundance patterns provide important clues about cosmic ray history and galactic chemical evolution. Astrochemical models increasingly incorporate cosmic ray effects to simulate molecular cloud chemistry accurately, star formation processes, and planetary system development. Observations across the electromagnetic spectrum, ranging from radio telescopes that detect molecular emission lines to ultraviolet and X-ray observatories, complement theoretical efforts, validating cosmic ray-induced chemistry in diverse environments. In laboratory experiments, researchers replicate cosmic ray irradiation of ices and dust analogs to understand chemical pathways relevant to space. These studies reveal the formation of complex organic molecules, including amino acids and nucleobase precursors, highlighting cosmic rays' potential role in the origin of life's building blocks. In sum, cosmic rays act as unseen sculptors of the universe's chemical landscape. Their penetrating ionizing power initiates and sustains a rich web of chemical interactions that fuel molecular complexity, influence thermal and dynamical states of cosmic structures, and ultimately contribute to the conditions necessary for star and planet formation. This invisible handiwork extends from the dark depths of molecular clouds to the surfaces of planets and the intergalactic medium, testifying to the profound and multifaceted impact cosmic rays exert beyond their energetic particle identity. With this understanding of their chemical influence, our journey will next explore how cosmic rays act as larger-scale sculptors, shaping the interstellar and circumgalactic mediums that govern the evolution of galaxies themselves, further illuminating their role as cosmic architects across the scales of the universe. Continuing our exploration of cosmic rays' profound influence on the universe, we arrive at an expansive and intricate domain where these energetic particles act as powerful sculptors of galaxies themselves. Beyond their roles as ionizing agents in interstellar chemistry, cosmic rays significantly shape the structure, dynamics, and evolution of the interstellar medium, ISM, the complex environment of gas, dust, and magnetic fields between stars, as well as the circumgalactic medium, CGM, the vast reservoirs of matter enveloping galaxies. In these cosmic arenas, cosmic rays interact with matter and magnetic fields to drive winds, regulate star formation, and mediate the large-scale feedback processes pivotal to galaxy evolution. The ISM is not a homogeneous expanse, but a multifaceted environment characterized by regions of varying densities, temperatures, and compositions. Cosmic rays permeate this medium, exerting pressure comparable to or even exceeding that of thermal gas and magnetic fields. This cosmic ray pressure influences the dynamics of gas clouds, helping to support them against gravitational collapse, or instead driving them into motion. One of the most significant effects cosmic rays have on the ISM is through the generation and sustaining of galactic winds, large-scale outflows of gas propelled from the galactic disk into the halo. These winds play an essential role in regulating star formation by removing gas, the raw material from which stars form, and enriching the CGM and intergalactic space with metals and other elements. Cosmic rays, due to their long mean free paths and ability to transfer momentum effectively to plasma via interactions with magnetic waves, can drive winds even in regions where thermal pressure would be insufficient. Recent magnetohydrodynamic simulations that incorporate cosmic ray physics demonstrate that these particles can launch and sustain winds over galactic scales, alter the gas cooling rates, and redistribute matter in complex ways. This cosmic ray-driven outflow phenomenon is crucial for explaining observations of galactic halos charged with diffuse, hot gas and the anisotropic distribution of baryonic matter. In metals-enriched circumgalactic media, cosmic rays participate in heating and ionizing the gas, affecting its observational signatures across the electromagnetic spectrum, from ultraviolet absorption lines to X-ray emission. Cosmic rays also influence the cycling of gas between the ISM and CGM. They modulate the balance between inflowing cold gas accretion from the intergalactic medium and outflowing winds, thereby governing the replenishment of star-forming material and the regulation of galactic growth. Without such cosmic ray-mediated feedback, models struggle to reproduce the stellar mass distributions and metallicity gradients observed in real galaxies. Furthermore, cosmic rays interact with magnetic turbulence throughout the ISM and CGM, contributing to the amplification and maintenance of galactic magnetic fields. These fields, in turn, affect the transport of cosmic rays themselves, creating a complex feedback loop wherein cosmic rays both shape and are shaped by the magnetized environment. This interplay is essential in stabilizing gas clouds, influencing the propagation of shocks, and determining the conditions under which new stars can form. On smaller scales, cosmic rays impact the structure and thermal pressure balance of molecular clouds, thereby affecting star formation rates and efficiency. By heating and ionizing gas within these clouds, cosmic rays regulate the chemistry and physical conditions necessary for gravitational collapse. Observationally, evidence of cosmic ray influence in shaping galactic environments emerges from multi-wavelength data. Gamma-ray observations detect diffuse emission produced by cosmic ray interactions with interstellar gas, providing maps of cosmic ray density and revealing their bulk propagation characteristics. X-ray and ultraviolet studies of galactic halos uncover hot, ionized gas linked to cosmic ray-driven winds and feedback. The circumgalactic medium represents a frontier where cosmic rays might also control the thermal and dynamical states of diffuse gas reservoirs, extending hundreds of thousands of light-years. These regions serve as intermediaries between galaxies and the vast intergalactic medium, making cosmic rays significant actors in the cosmic baryon cycle and galaxy ecosystem. Looking forward, theoretical models and cosmological simulations continue to evolve, incorporating increasingly sophisticated treatments of cosmic ray transport, energy losses, and feedback effects. These efforts provide critical comparisons with observational data, enhancing our understanding of how cosmic rays affect galaxy evolution across diverse environments and epochs. In the grand design of the cosmos, cosmic rays emerge not only as remnants of violent astrophysical processes, but also as dynamic agents intricately influencing the evolution of galaxies. By shaping the interstellar and circumgalactic mediums, they contribute to the cosmic ballet of matter, energy, and magnetic fields that give rise to the stars, planets, and ultimately, the conditions amenable to life. Our journey next turns inward to explore how cosmic rays intimately influence individual stars, altering their evolution, dynamics, and ultimate fates, further amplifying their role as universal architects across scales. As we continue our cosmic journey, we now turn our attention to a more intimate scale. How cosmic rays, these energetic travelers from the depths of space, interact with and influence the life cycles of stars themselves. Stars are the grand furnaces of the universe, forging elements and radiating energy. But within these complex beings, the subtle yet profound effects of cosmic rays ripple through, altering their evolution, behavior, and ultimate fate. Understanding how cosmic rays influence stellar evolution unveils new layers to the cosmic relationship between high-energy particles and the oldest light of the cosmos. Stars form within dense molecular clouds, regions rich with gas and dust, where gravity pulls matter inward until nuclear fusion ignites. Cosmic rays play an important role even in these stellar birthplaces. By penetrating deep into these clouds, cosmic rays interact with the dense gas, providing a persistent source of ionization. This ionization influences the balance between the forces tending to collapse the cloud and those resisting collapse, acting as a regulator of star formation rates. In environments partially shielded from stellar ultraviolet radiation, cosmic rays initiate chemical reactions, altering the cloud's molecular makeup and thereby modifying conditions for star formation. Once a star is born and begins its nuclear burning, cosmic rays continue to exert influence, particularly for stars immersed in environments with elevated cosmic ray fluxes, such as near supernova remnants or in energetic starburst regions. Cosmic rays can penetrate the outer atmospheres and magnetospheres of stars, depositing energy and driving additional ionization. These processes can affect the stellar wind, powerful streams of charged particles emitted from a star that shapes the star's immediate surroundings and influences angular momentum loss. For massive stars, whose tumultuous lives end in spectacular supernova explosions, cosmic rays play roles during both the main sequence and supernova phases. The enhanced ionization levels due to cosmic rays can increase coupling between ionized material and magnetic fields, affecting convection and mixing processes within the star. This can alter nucleosynthesis pathways, influencing the synthesis of elements and isotopes. In the late stages of stellar evolution, as stars shed their outer layers to form planetary nebulae, or during the intense wind phases of massive stars, cosmic rays contribute to shaping the circumstellar environments. They can drive chemical reactions and ionization in the ejected material, influencing its temperature, density, and dynamics. These effects determine how the enriched matter mixes with the interstellar medium, enriching future generations of stars and planets. Moreover, cosmic rays can mediate magnetic turbulence within stellar interiors and atmospheres, affecting the transport of energy and particles. This turbulence can influence stellar magnetic dynamo processes, which govern magnetic field generation and variability, a key factor in phenomena like stellar spots, flares, and cycles. In the context of stellar remnants such as neutron stars and white dwarfs, cosmic ray interactions continue. Pulsars, rotating neutron stars with intense magnetic fields, emit powerful particle winds in which cosmic rays are both accelerated and affected. These winds influence the surrounding nebulae, contributing to the high-energy astrophysical phenomena observable across the electromagnetic spectrum. Observationally, the interplay between cosmic rays and stars is studied through emission signatures, such as gamma rays, X-rays, and specific molecular line emissions that reveal ionization states and chemical changes in stellar environments. These data provide insights into the cosmic ray fluxes impacting stars and the resulting astrophysical consequences. On the theoretical front, models of stellar evolution increasingly incorporate cosmic ray ionization and feedback effects, refining predictions of stellar lifetimes, spectral characteristics, and end states. Simulations exploring star formation in high cosmic ray flux environments illustrate delayed or enhanced star formation scenarios, depending on ionization and thermal feedback. In our own solar environment, cosmic rays influence the Sun's atmosphere and the heliosphere, contributing to space weather and affecting planetary atmospheres across the solar system. These localized effects intimate the broader cosmic influences that cosmic rays wield at varied scales. As we consider the vast cosmic canvas, it becomes evident that cosmic rays are not mere bystanders in stellar evolution, but active participants shaping the life cycles of stars. By modifying ionization, chemistry, magnetic fields, and energy transport, they weave subtle yet significant threads into the grand narrative of stellar genesis, growth, and demise. Our next step in this cosmic odyssey is to explore the fundamental process of element creation itself, nucleosynthesis. We will examine how cosmic rays contribute to forging the elements, blending astrophysics and nuclear physics into the alchemy that creates the universe's rich chemical diversity. Our cosmic journey now brings us to the elemental heart of the universe, the process by which the basic building blocks of matter come into existence, known as nucleosynthesis. This sublime cosmic alchemy, occurring in stars, supernovae, and even through interactions involving cosmic rays themselves, is fundamental to the chemistry of the universe. In this chapter, we explore how cosmic rays contribute uniquely to the forging of elements, complementing the stellar furnaces and explosive events that have long been known as the universe's elemental forges. The term nucleosynthesis encompasses the various nuclear processes that create atomic nuclei from protons and neutrons. It primarily occurs in three major contexts: primordial nucleosynthesis, during the first few minutes after the Big Bang; stellar nucleosynthesis within the cores of stars during their lifetimes; and explosive nucleosynthesis in events like supernovae and neutron star mergers. Cosmic rays, however, contribute to yet another distinct and essential channel: spallation nucleosynthesis. Cosmic ray spallation is a process whereby high-energy cosmic ray particles, mostly protons and alpha particles, collide with nuclei of interstellar gas, especially heavier elements like carbon, nitrogen, and oxygen. These collisions, energetic and violent, break apart the target nuclei into lighter elements, effectively chipping away fragments. This interaction produces certain rare light elements such as lithium, As, beryllium, Be, and boron, B, which are not abundantly synthesized in standard stellar nucleosynthesis or primordial processes. The observed abundances of these light elements in the galaxy cannot be fully explained without invoking cosmic ray spallation. By measuring their distribution and isotopic ratios, astrophysicists validate spallation models and gain insights into cosmic ray fluxes and propagation history. This establishes cosmic rays as critical agents not only for their energetic properties, but also as contributors to elemental evolution. Stellar nucleosynthesis, while distinct from cosmic ray nucleosynthesis, intertwines with cosmic rays in meaningful ways. The processes within stars, from hydrogen fusion in main sequence stars to the advanced stages of helium, carbon, and heavier element fusion, build most of the periodic table. Cosmic rays, through their interactions with stellar winds, ejecta, and supernova shock fronts, influence isotopic compositions by initiating further nuclear reactions and modifying the composition of interstellar medium feeding future generations of stars. Explosive nucleosynthesis during supernovae and neutron star mergers involves rapid neutron capture, the ER process, and slow neutron capture, the S process, producing many of the heavy elements beyond iron. Cosmic rays themselves are, in turn, accelerated in these violent environments, linking nucleosynthesis directly to high-energy particle physics. Another intriguing aspect is cosmic ray interactions within planetary atmospheres and surfaces, where they induce secondary nuclear reactions that produce cosmogenic isotopes, such as carbon-14 and beryllium-10. These isotopes are invaluable in dating geological and cosmological processes, creating a bridge from cosmic nucleosynthesis to Earth sciences. Current research also explores the potential contribution of cosmic rays to prebiotic chemistry by modifying the elemental and isotopic composition of interstellar and circumstellar matter, seeding the molecular precursors to life. The study of nucleosynthesis through the prism of cosmic rays is supported by increasingly sophisticated observational and experimental methods. High-resolution spectroscopy allows astronomers to detail elemental and isotopic abundances in distant stars and the interstellar medium. Particle accelerators simulate cosmic ray collisions for nuclear reaction cross-section measurements, refining theoretical models. In uniting the stellar processes with cosmic ray phenomena, Nucleosynthesis underscores a fundamental unity in the cosmic narrative: how energy, matter, and nuclear physics interplay to build the universe's chemical complexity. Cosmic rays serve as both the hammers breaking nuclei in spallation and the energetic witnesses to the most intense nucleosynthetic sites. From the primordial hydrogen and helium forged in the Big Bang to the complex elements fostering planets and life, nucleosynthesis is a saga of continuous transformation. Cosmic rays, often overlooked in this story, emerge as invisible forgers, shaping elemental abundances and imprints across space and time. As we further explore the interconnected universe, the next segment will examine the subtle but profound relationship between cosmic rays and the cosmic microwave background, the relic radiation of the Big Bang, and how these interactions link the smallest particles to the universe's largest-scale structure and history. As we venture further into the cosmic tapestry woven by high-energy particles, we encounter a profound connection between cosmic rays and one of the most significant relics of the universe's infancy: the cosmic microwave background, CMB. This faint afterglow of the Big Bang permeates all of space, serving as a backdrop against which cosmic rays, the energetic messengers from distant astronomical accelerators, embark on their intergalactic journeys. The interactions between cosmic rays and the CMB not only shape our understanding of particle physics and astrophysics, but also provide critical constraints on the origins and propagation of the highest energy cosmic rays observed. The cosmic microwave background is the residual thermal radiation dating back to roughly 380,000 years after the Big Bang, when the universe cooled sufficiently for photons to decouple from matter and travel freely through space. The CMB exhibits a nearly perfect blackbody spectrum at a temperature of about 2.7 Kelvin, filling the cosmos homogeneously and isotropically. While this background radiation is incredibly uniform, its slight anisotropies have been studied in exquisite detail, revealing clues about the early universe's structure and evolution. For cosmic rays, particularly the ultra-high-energy cosmic rays, UHCRs, with energies surpassing 10^19 electron volts, the CMB acts as an inescapable cosmic obstacle and interaction partner. As these energetic particles traverse intergalactic space, they encounter a pervasive bath of low-energy CMB photons. At sufficiently high energies, cosmic ray protons interact with these photons via processes such as photopion production, leading to energy losses through the creation of pions and other secondary particles. This effect, first predicted independently by Greisen, Zatsepin, and Kuzmin in the mid-1960s, results in an energy attenuation mechanism known as the GZK cutoff. The GZK effect limits the distance that UHCRs can travel before their energy drops below a certain threshold, effectively setting a horizon beyond which cosmic rays cannot reach Earth at their original ultra-high energies. This theoretical prediction has profound implications for the identification of cosmic ray sources and the structure of the nearby universe. Detecting the GZK cutoff and analyzing the cosmic ray spectrum's suppression at the highest energies has been a major scientific milestone for modern observatories, such as the Pierre Auger Observatory and the Telescope Array. These findings corroborate the fundamental role the CMB plays in modulating cosmic ray propagation and delineate the cosmic neighborhood accessible via ultra-high-energy cosmic ray astronomy. Beyond energy losses, interactions between cosmic rays and CMB photons produce secondary particles, including neutrinos and gamma rays, which propagate unimpeded and serve as vital messengers in multi-messenger astrophysics. These cosmogenic neutrinos, generated through photopion decay pathways triggered by the cosmic ray CMB interactions, offer complementary avenues for probing the origins and compositions of the highest energy cosmic rays. Neutrino observatories like IceCube and its successors continue to seek these elusive particles, striving to unravel the complex interplay between cosmic rays and the cosmic background radiation. Furthermore, the influence of the CMB extends to cosmic ray nuclei heavier than protons. Photodisintegration processes occur when ultra-relativistic nuclei absorb CMB photons, leading to the emission of nucleons and altering the nuclear composition during their journey. This phenomenon modifies the expected cosmic ray elemental spectrum as observed on Earth and informs models of cosmic ray source distributions and acceleration mechanisms. At a more fundamental level, cosmic ray interactions with the CMB offer a unique natural particle physics laboratory probing extremely high-energy regimes inaccessible by terrestrial accelerators. The physics underlying photopion production and nuclear disintegration in this context provide tests of particle interaction cross-sections and theories beyond the standard model, extending our knowledge of high-energy astrophysical phenomena. Additionally, the presence of the CMB shapes large-scale cosmic magnetic fields and influences the structure of the intergalactic medium, factors that impact cosmic ray diffusion and anisotropy. The radiation field modulates cosmic ray transport indirectly by governing the energy losses and thereby affecting their distribution and arrival directions. In summary, the cosmic microwave background is not a distant relic disconnected from present-day cosmic ray physics, but an active participant in shaping the energy spectrum, composition, and global propagation of cosmic rays. This intimate connection integrates cosmology, high-energy astrophysics, and particle physics into a coherent narrative elucidating the boundaries and possibilities of cosmic ray astronomy. Our next exploration will bring us closer to home, examining how cosmic rays influence Earth's atmosphere, inducing subtle yet significant changes in atmospheric processes, weather patterns, and climate systems. This chapter unveils the nexus between cosmic-scale phenomena and terrestrial environments, demonstrating once more the far-reaching impact of cosmic rays across the scales of space and life. As we shift our gaze from the vastness of space to the protective envelope surrounding our planet, it becomes evident that cosmic rays, though born in the most energetic corners of the universe, also exert subtle yet profound influence on Earth's atmosphere and weather systems. Far from mere high-energy visitors, cosmic rays play a role in atmospheric chemistry, cloud formation, and even climate variability. This chapter explores the intricate relationship between cosmic rays and Earth's atmospheric processes, revealing an intimate connection between solar system environment and terrestrial phenomena. Cosmic rays impacting Earth's atmosphere primarily consist of high-energy protons and heavier nuclei traveling at near-light speeds. When these particles collide with molecules in the upper atmosphere, mostly nitrogen and oxygen, they initiate cascades of secondary particles, initiating extensive air showers. These interactions generate ionization, producing free electrons and ions that significantly affect the electrical properties of the atmosphere. This ionization creates charged aerosol particles, which act as cloud condensation nuclei, CCN. The presence and abundance of CCN influence cloud microphysical properties, affecting cloud droplet formation, cloud reflectivity, albedo, and precipitation processes. In essence, cosmic rays indirectly modulate the extent and characteristics of cloud cover, with cascading implications for Earth's energy balance and, potentially, its climate. One of the earliest hypotheses linking cosmic rays to climate emerged in the mid-20th century, brought into prominence by physicist Henrik Svensmark and collaborators. They proposed that variations in cosmic ray flux, caused by changes in solar activity and geomagnetic conditions, lead to corresponding changes in low cloud cover, thereby influencing global temperatures. This cosmic ray cloud connection has driven extensive research and debate, inspiring numerous observational and modeling studies. Observational data have revealed correlations between cosmic ray flux variations and changes in cloud cover and, in some cases, weather patterns. Ground-based neutron monitors, satellite cloud imaging, and atmospheric ionization measurements have been employed to investigate these links. However, disentangling the cosmic ray influence from other atmospheric and solar drivers remains complex, with factors such as solar ultraviolet radiation, aerosols from volcanic eruptions, and greenhouse gases contributing simultaneously to climate variability. Beyond cloud dynamics, cosmic rays influence atmospheric chemistry by facilitating the formation of reactive ions and radicals. These species participate in catalytic reactions that modulate trace gases, including ozone, nitric oxide, and hydroxyl radicals. Ozone dynamics, in turn, are crucial for regulating the amount of ultraviolet radiation reaching Earth's surface, impacting biological and chemical processes. Cosmic rays also play a role in the global electric circuit, a planetary-scale electrical system in which thunderstorm activity generates electric currents that flow through the ionosphere and down to the Earth's surface. Ionization from cosmic rays maintains conductivity in the atmosphere, enabling current flow between cloud tops and the ionosphere, linking cosmic phenomena to terrestrial electrical environments. Solar activity modulates cosmic ray flux through solar wind and heliospheric magnetic field variations. During periods of high solar activity, solar maxima, intensified solar wind and magnetic turbulence deflect a larger fraction of galactic cosmic rays, reducing ionization rates in Earth's atmosphere. Conversely, solar minima allow increased cosmic ray penetration. This modulation coincides with measurable changes in atmospheric ionization, cloud cover patterns, and potentially climate variations on decadal timescales. Space weather events, including solar proton events and geomagnetic storms, introduce energetic particles into Earth's magnetosphere and atmosphere, causing localized increases in radiation levels and ionization. These transient phenomena can affect atmospheric chemistry and dynamics, influencing phenomena such as polar stratospheric ozone depletion and ionospheric disturbances. Laboratory experiments such as the Cloud, Cosmics Leaving Outdoor Droplets, project at CERN simulate cosmic ray ionization effects under controlled conditions. These studies provide valuable insights into nucleation processes and the role of cosmic rays in aerosol and cloud droplet formation, enhancing mechanistic understanding foundational to atmospheric models. Meteorological models increasingly integrate cosmic ray ionization parameters to simulate their influence on microphysical cloud processes and larger-scale weather systems. While uncertainties remain regarding the magnitude and climatic significance of cosmic ray effects, the integration of astrophysical factors into Earth system science illustrates the growing interdisciplinary nature of climate research. Ultimately, cosmic rays exemplify a profound planetary connection. Particles born in distant astrophysical accelerators influence the physical and chemical properties of our atmosphere, affecting clouds, weather patterns, and possibly climate evolution. This cosmic terrestrial interplay reflects the interconnectedness of phenomena across vast spatial and temporal scales. As we move further along our cosmic narrative, the next chapter delves into the role cosmic rays have played in the story of life itself, their contribution to genetic mutations, evolution, and the emergence of biological diversity, underscoring once again their pervasive influence from the microscopic to the cosmic scale. In the intricate web of cosmic phenomena that shape our universe, cosmic rays emerge not only as powerful agents of physics and astrophysics, but also as subtle architects of life itself. From the depths of space, these high-energy particles incessantly bombard Earth, interacting with its atmosphere and biosphere in ways that have helped sculpt the very fabric of biological evolution. As we delve into the profound relationship between cosmic rays, genetic mutation, and the emergence and evolution of life, we uncover yet another layer where the macrocosm intertwines with the microcosm to influence our own biological destiny. Life, as we understand it, is driven in no small part by the delicate balance between genetic stability and variability. Mutations, changes in the DNA sequence, are the raw material of evolution, enabling organisms to adapt, diversify, and survive in a changing environment. While many mutations arise from internal cellular processes or chemical exposures, external sources of ionizing radiation also contribute to the mutation landscape. Cosmic rays, with their potent capability to ionize biological molecules, stand as one of the most significant natural sources of such mutagenic radiation. When cosmic rays collide with the Earth's atmosphere, they generate cascades of secondary particles, including neutrons, protons, muons, and electrons, which reach the surface and penetrate living tissues. These secondary particles can interact directly with DNA, causing strand breaks, cross-links, or base modifications. Some of these damages, if unrepaired or misrepaired, lead to mutations. The high linear energy transfer, LET, characteristic of certain cosmic ray components, particularly heavy ions known as high charge and energy, HZE particles, fosters dense ionization tracks within cells, making the resulting damage complex and biologically impactful. Throughout Earth's history, cosmic ray-induced mutations have interacted with other evolutionary forces, such as natural selection and genetic drift, to influence adaptation processes. For example, evolving organisms have developed sophisticated DNA repair mechanisms precisely because external mutagenic pressures, including cosmic rays, necessitate genomic maintenance. Variations in cosmic ray flux over geological timescales, from solar activity fluctuations to changes in Earth's magnetic shielding and atmospheric thickness, potentially contributed to episodic bursts of increased mutation rates, which may correlate with evolutionary events. Indeed, paleontological and geological records hint at connections between changes in cosmic ray intensity and biological evolutionary milestones. Some hypotheses suggest that increased cosmic radiation during periods of reduced geomagnetic field strength or heightened solar activity could have accelerated mutation rates sufficiently to influence speciation or extinction patterns. While establishing definitive causal relationships remains an active field of research, the plausibility and scope of cosmic ray influence on life's diversification are compelling. Beyond mutation, cosmic rays may also play a role in prebiotic chemistry, the chemical processes believed to have led to the origin of life. Laboratory simulations exposing primordial Earth-like atmospheres and ices to cosmic ray analogs demonstrate the synthesis of complex organic molecules, including amino acids and nucleobases, the building blocks of proteins and nucleic acids. This suggests that cosmic rays contributed energy necessary for the chemical evolution that led to the first living systems. Moreover, cosmic rays continue to affect living organisms today, with epidemiological and experimental studies investigating health effects, ranging from cancer risks to developmental changes. Understanding cosmic ray biology has practical implications for space travel, where increased exposure presents challenges for astronaut health and for assessing radiation risk on Earth. On an ecological scale, interactions between cosmic rays, cloud formation, and climate, as discussed earlier, may indirectly influence habitats, biodiversity, and evolutionary pressures. Changes in weather patterns driven by cosmic ray flux could modulate environmental selection forces, influencing evolutionary trajectories. The dual nature of cosmic rays as both agents of genetic damage and facilitators of organic chemistry exemplifies the complex interplay between destructive and creative forces in the universe. Their pervasive presence throughout Earth's history links the cosmic environment to biological fate, situating life firmly within a universal context. As we reflect on the profound role cosmic rays play in mutation and evolution, our journey proceeds to examine their interaction with Earth's magnetic shields, how these invisible guardians modulate cosmic ray exposure and protect the biosphere, even as they shape the delicate balance between cosmic influence and planetary habitability. This exploration reveals another critical facet of cosmic rays' role in shaping life on our planet, and demonstrates the complex interplay between cosmic phenomena and Earth's natural defenses. As we have seen, cosmic rays are powerful, high-energy particles journeying through space from distant astrophysical sources, continuously bombarding Earth's atmosphere. Yet, despite their penetrating nature and potential dangers, our planet's survival, and indeed the flourishing of life itself, depends significantly on a remarkable natural defense: Earth's magnetic shield. This invisible guardian shapes the cosmic ray environment close to our planet, acting both as a protective barrier and, intriguingly, as a complex gatekeeper that modulates the cosmic ray flux reaching Earth's surface. This section explores this delicate balance, illustrating how Earth's magnetic field simultaneously defends against cosmic ray hazards, while also subtly influencing our exposure to these energetic particles. The Earth is enveloped in a magnetic field generated by the motions of molten iron within its outer core, a geodynamo that creates a dipolar magnetic field extending tens of thousands of kilometers into space. This magnetic field forms the magnetosphere, a protective bubble that deflects charged particles originating from the Sun and the cosmos, including cosmic rays. The magnetosphere acts as the planet's first line of defense against high-energy radiation. Cosmic rays are charged particles, mostly protons and atomic nuclei, and thus their paths are strongly influenced by magnetic fields. When these energetic particles encounter the Earth's magnetic field, they experience Lorentz forces that bend their trajectories. Low-energy cosmic rays are more susceptible to deflection and are often prevented from entering the atmosphere. It's a cosmic sieve that filters out particles beneath a certain rigidity threshold, known as the geomagnetic cutoff. This geomagnetic cutoff is not uniform globally. Near the magnetic poles, field lines plunge almost vertically into the atmosphere, allowing cosmic rays easier access along these open funnels. Conversely, near the magnetic equator, where field lines are more horizontal, the cutoff rigidities are higher, providing stronger shielding. This phenomenon leads to a global spatial variation in cosmic ray flux, with polar regions receiving significantly higher intensities, a fact crucial for understanding radiation environments at different latitudes. However, Earth's magnetic shield is not static. It fluctuates over various timescales, from daily interactions of the magnetosphere with solar wind and coronal mass ejections, to long-term changes in the magnetic field's intensity and configuration. During geomagnetic storms triggered by solar activity, the magnetosphere's protective efficacy is temporarily impaired, allowing increased cosmic ray fluxes at lower latitudes and sometimes intensifying space weather effects. On geological timescales, Earth's magnetic field has undergone numerous polarity reversals and excursions, periods where the field weakens or vanishes temporarily. These episodes potentially increase cosmic ray penetration to the surface, influencing atmospheric chemistry and possibly biological mutation rates. Paleomagnetic studies reveal correlations between field strength variations and isotopic evidence of cosmic ray flux changes, underscoring the vital dynamic role of Earth's magnetic shield. Moreover, the magnetosphere works synergistically with the atmosphere, adding an additional layer of protection. While the magnetosphere deflects many charged particles, some energetic cosmic rays penetrate and initiate cascades in the atmosphere, as discussed earlier. Together, these defenses reduce surface radiation levels to those compatible with life. Despite its protective role, Earth's magnetic field also acts as a guardian enabling scientific investigation. By modulating cosmic ray intensity, it provides conditions essential for observing cosmic ray variations linked to solar cycles, geomagnetic activity, and extraterrestrial phenomena. Understanding these variations helps space weather forecasting and radiation risk assessment, critical for aviation, satellite operation, and human spaceflight. Interestingly, the polar regions, with enhanced cosmic ray flux, become natural laboratories for studying cosmic ray interactions and effects on atmospheric processes, including auroras and ionospheric dynamics. These regions also present increased radiation risks for high-latitude aviation and missions. As human technology and exploration extend beyond Earth's protective magnetosphere into deep space, the absence of this magnetic shield highlights the importance of artificial protection against cosmic rays. Understanding Earth's magnetic shielding mechanisms informs the design of spacecraft shielding and mission planning, underscoring our continued reliance on this natural guardian. In summary, Earth's magnetic field acts both as a formidable shield that mitigates the potentially harmful effects of cosmic rays and as a modulator that shapes the radiation environment, influencing atmospheric chemistry, weather, and biological systems. Its dynamic nature and interactions with cosmic rays weave a complex narrative of protection and exposure that has profound implications for life on Earth and for humanity's ventures into space. Moving forward, we shall explore how researchers map the anisotropy, subtle directional variations, in cosmic ray arrivals, probing traces of their cosmic origins and further elucidating the interplay between cosmic rays, magnetic fields, and the structure of the universe. Having examined the protections offered by Earth's magnetic shield against cosmic rays, we now shift our focus to a subtle yet powerful tool used by astrophysicists to unravel the origins of these cosmic messengers: the mapping of anisotropy in cosmic ray arrival directions. Although cosmic rays batter our planet isotropically, appearing to come evenly from every direction, careful measurements reveal slight anisotropies, or directional irregularities, in their flux. These subtle variations serve as critical fingerprints, providing indirect but invaluable clues about the cosmic sources and propagation paths of cosmic rays, and helping to untangle the complex interplay between astrophysical accelerators, magnetic fields, and interstellar space. Because cosmic rays are charged particles, their trajectories through space do not follow straight lines. They spiral, bend, and scatter due to interactions with magnetic fields both within the Milky Way and in extragalactic space. This magnetic deflection generally erases direct correlations between the arrival direction of cosmic rays and their astrophysical sources, especially at lower energies where their gyroradii are small. However, at higher energies, particularly in the ultra-high energy cosmic ray regime exceeding 10^18 electron volts, deflections decrease, allowing the possibility that some anisotropic signatures persist. Mapping anisotropy requires extremely sensitive detectors with enormous exposure times to accumulate statistically significant datasets. Large observatories, such as the Pierre Auger Observatory in Argentina and the Telescope Array in Utah, record millions of cosmic ray events, enabling scientists to analyze arrival directions at fine angular resolution. These analyses search for deviations from perfect isotropy, revealing large-scale patterns and localized excesses across the sky. One of the most prominent features observed is a dipolar anisotropy, a slight but measurable excess of cosmic rays arriving preferentially from a specific general direction, with a corresponding deficit in the opposite sky region. At energies around 10 or 8 or 10 or 19 or Vi, studies detect such dipolar patterns, suggesting a shift in dominant cosmic ray origins or propagation effects. The dipole points roughly away from the galactic center, consistent with a transition from galactic to extragalactic sources. Smaller-scale anisotropies also emerge. Some analyses report localized. Our journey through the realm of cosmic rays now takes us to an extraordinary frontier where astrophysics and particle physics intertwine. The study of ultra-high-energy cosmic rays, UHECRs. These rare particles possess energies millions of times greater than those achievable by Earth's most powerful particle accelerators, effectively turning the cosmos itself into a vast natural laboratory, a particle collider stretching across intergalactic distances. In this chapter, we explore the nature, origin, detection, and profound significance of these ultra-high-energy travelers, revealing how they test fundamental physics and challenge our understanding of particle acceleration in the universe. Ultra-high-energy cosmic rays are defined by energies exceeding approximately 10 to 18 electron volts, eV, and reaching upwards of 10 to 20 electron volts or more. To put this astonishing scale into perspective, the Large Hadron Collider, the most powerful man-made accelerator, operates at collision energies near 10 to 13 electron volts. The energies carried by UHECRs dwarf these, offering access to physical regimes unattainable in terrestrial experiments, opening windows into particle interactions at extreme energies. The sources of UHECRs remain one of the most tantalizing mysteries in astrophysics. Their extreme energies imply acceleration in the most violent and energetic cosmic environments. Candidate astrophysical accelerators include active galactic nuclei, AGN, with relativistic jets, gamma-ray bursts, GRBs, fast-spinning newborn neutron stars, and even more exotic hypothetical phenomena such as topological defects or the decay of supermassive relic particles from the early universe. One core difficulty in pinpointing the origins of UHECRs arises from magnetic deflections. Though at these ultra-high energies, particles have larger gyroradii, enabling more direct trajectories, magnetic fields both within the Milky Way and intergalactic space still cause some deflections, blurring source identifications. Thus, deciphering anisotropies, spatial variations in arrival directions, is critical for source localization efforts. Detection of UHECRs is primarily indirect due to their scarcity and atmospheric interactions. As UHECRs slam into Earth's atmosphere, they generate extensive air showers, cascades of secondary particles spreading over several square kilometers. Observatories like the Pierre Auger Observatory and the Telescope Array deploy vast arrays of detectors and fluorescence telescopes to capture these extensive air showers, reconstructing the cosmic rays' arrival direction, energy, and composition. Through meticulous measurements, scientists have characterized several key features of the UHECR energy spectrum. Notably, the observed flux steepens sharply above 510 EV, consistent with the predicted Greisen-Zatsepin-Kuzmin (GZK) cutoff, an energy threshold beyond which cosmic rays lose energy interacting with the cosmic microwave background photons. This effect limits the effective horizon of UHECRs, suggesting nearby extragalactic sources as their origins. Composition measurements indicate a complex mixture of protons and heavier nuclei at ultra-high energies, with composition trends varying as a function of energy. Understanding these mixings informs acceleration physics and source characteristics, constraining theoretical models. UCHIKRs also offer an unparalleled probe into particle physics at extreme energies. By analyzing extensive air shower properties, scientists infer hadronic interaction cross-sections and particle multiplicities beyond collider reach, testing and refining high-energy physics theories and interaction models. Moreover, secondary particles accompanying U-checker interactions, photons and neutrinos, serve as complementary messengers, initiating the field of multi-messenger astrophysics. Detecting cosmogenic neutrinos produced during cosmic ray propagation could provide direct insights into U-checker composition and source distributions, a frontier actively pursued by neutrino observatories like IceCube. Despite these advances, many mysteries endure. The exact locations and mechanisms of U-checker acceleration, the role of magnetic fields in propagation, and the reconciliation of composition and spectrum measurements remain active research areas. New generation observatories and proposed space missions promise to increase detection statistics and precision, aiming to resolve these enigmas. In essence, ultra-high-energy cosmic rays transform the vast cosmos into a grand particle collider, delivering natural experiments at unparalleled energies and distances. Their study pushes the boundaries of astrophysics and fundamental physics, deepening our understanding of the universe's most energetic processes. Our next exploration will delve into the unresolved puzzles surrounding these cosmic rays, including the notable GZK cutoff phenomenon and the intriguing absence of corresponding cosmic ray sources at the highest energies. These mysteries challenge our current knowledge and beckon the next leap in cosmic ray science. As we delve deeper into the frontier of cosmic ray research, we confront two of the most perplexing and enduring mysteries: the Greisen-Zatsepin-Kuzmin (GZK) cutoff and the enigma of missing sources for ultra-high-energy cosmic rays (UHECRs). Despite tremendous advances in detection technologies and theoretical models, these puzzles challenge our understanding of cosmic ray origins, propagation, and the structure of the universe itself. This chapter explores the nature of these unresolved questions, the current state of research, and the scientific efforts aimed at solving them. The GZK cutoff, predicted independently by Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin in 1966, is a theoretical limit on the maximum energy of cosmic rays that can reach Earth from distant sources. It arises from interactions between ultra-high-energy protons and the pervasive cosmic microwave background, CMB, radiation. When cosmic rays with energies exceeding approximately 5 × 10⁻19 electron volts collide with low-energy CMB photons, they experience energy losses through processes such as photopion production, producing pions, and reducing their kinetic energy. This energy attenuation implies that cosmic rays above the GZK threshold cannot travel more than roughly 100 megaparsecs, about 300 million light-years, without losing significant energy. Consequently, the observed population of the highest energy cosmic rays should originate from relatively nearby extragalactic sources. This sets a natural horizon in the cosmos for detecting U-checkers at Earth. While several experiments, including the Pierre Auger Observatory and the Telescope Array, have reported a suppression in the cosmic ray energy spectrum consistent with the GZK cutoff, the measured spectrum exhibits features and event rates that provoke ongoing debate. Notably, the detailed shape of the cutoff and the composition of cosmic rays near this energy remain areas of active investigation, with implications for acceleration mechanisms and source distributions. Equally confounding is the so-called missing sources problem. Given the GZK horizon limit, there should be identifiable astrophysical objects, such as active galactic nuclei, AGN, starburst galaxies, or other powerful accelerators within a few hundred million light-years that are responsible for producing the highest energy cosmic rays. However, despite extensive surveys and correlation studies, the observed arrival directions of UHECers do not conclusively trace back to known, nearby candidate sources. This absence of definitive sources challenges existing models of cosmic ray origin and propagation. Several hypotheses have been proposed to address the missing sources puzzle. One possibility is that magnetic deflections, even at ultra-high energies, are sufficient to obscure source directions, especially if cosmic rays are heavier nuclei rather than protons. Another theory suggests that unknown or yet undiscovered astrophysical accelerators within the GZK radius may be responsible. Alternatively, exotic physics scenarios, such as the decay of super-heavy dark matter particles or topological defects, have been invoked. Furthermore, the interplay between cosmic ray composition, source evolution, and propagation effects complicates the interpretative landscape. For example, heavier nuclei experience different interactions and energy losses during transit, affecting arrival energy spectra and directionality. These complexities necessitate refined models incorporating particle physics, astrophysics, and cosmology. The uncertainties extend to the generation of secondary particles such as neutrinos and gamma rays produced during propagation. Detecting these cosmogenic particles is crucial for multi-messenger approaches that could unveil the nature of UHECer sources and their distribution. Advancements in detection capabilities, including larger ground arrays, more sensitive fluorescence telescopes, and space-based observatories like the proposed POEMA mission, aim to increase event statistics and directional resolution. Complementary neutrino and gamma-ray observatories enhance the prospects of pinpointing sources through multi-messenger astronomy. Despite decades of research, the GZK cutoff and missing sources remain compelling astronomical riddles. They embody the challenges of exploring extreme physics at cosmic scales and the limitations imposed by both nature and our current technologies. In confronting these mysteries, scientists continue to push the boundaries of observational prowess and theoretical innovation, motivated by the profound significance of understanding cosmic ray origins, the mechanisms accelerating particles to unfathomable energies, and the broader narratives of cosmic evolution. Our next step in this cosmic odyssey is to investigate the cutting-edge tools and next-generation observatories designed to unravel these puzzles, illuminating the path toward future discoveries in cosmic ray science. The study of cosmic rays has continuously pushed the boundaries of technology and scientific inquiry, revealing secrets of the universe from the tiniest subatomic particles to the grandest cosmic structures. Yet, as we've uncovered in previous chapters, many fundamental questions about cosmic rays remain unresolved, demanding ever more sensitive detectors, innovative observational techniques, and sophisticated analytical tools. To rise to this challenge, the scientific community is pioneering a new generation of observatories and research initiatives designed to unlock the deepest mysteries and broaden our cosmic horizon. Next-generation observatories build upon the successes and lessons learned from decades of cosmic ray detection, capitalizing on technological advancements in detector design, data processing, and multi-messenger astrophysics. These ambitious projects seek to enhance sensitivity, energy range, and directional resolution, enabling precise mapping of cosmic ray sources, detailed composition analyses, and comprehensive understanding of propagation effects. One cornerstone of future cosmic ray research is the upgrade and expansion of ground-based facilities. The Pierre Auger Observatory, the world's largest cosmic ray detector, is undergoing a major enhancement known as Auger Prime. This upgrade integrates new scintillator detectors atop existing water Cherenkov tanks to improve composition sensitivity. By distinguishing between light and heavy nuclei more effectively, Auger Prime aims to unravel the perplexing puzzle of cosmic ray origins and their acceleration mechanisms. Similarly, the telescope array collaboration is advancing its experimental setup with increased detector density and enhanced fluorescence detection capabilities, striving for complementary measurements to Auger and better characterization of cosmic rays arriving from the northern hemisphere. Beyond Earth's surface, space-based cosmic ray observatories promise unprecedented exposures and unique observational vantage points. Missions like the planned POEMA, probe of extreme multi-messenger astrophysics, envision deploying satellites capable of detecting ultra-high-energy cosmic rays and neutrinos by capturing atmospheric fluorescence and Cherenkov signals from orbit. This global coverage and rapid response capability drastically expand detection rates, revolutionizing our capacity to observe rare but informative cosmic ray events. The continued operation and upgrades of instruments aboard the International Space Station, such as the Alpha Magnetic Spectrometer, AMS-02, also remain vital, providing precise measurements of cosmic ray composition and flux over extended periods, free from atmospheric distortion. Proposed successors aim to extend energy coverage and improve charge resolution. Complementing cosmic ray observatories, neutrino detectors like IceCube and its planned extensions, IceCube GN2, as well as water-based Cherenkov detectors, facilitate multi-messenger approaches by detecting neutrinos that travel vast cosmic distances unimpeded. These neutrinos hold clues about hadronic interactions at the source, bridging cosmic ray physics with high-energy astrophysics. Radio detection of air showers is another burgeoning field, with arrays like LOFAR and planned dense antenna deployments enhancing sensitivity to cosmic ray-induced radio emission. The relative cost-effectiveness and wide coverage of radio methods promise significant expansions in air shower detection and energy resolution. Data science and simulation frameworks are crucial tools underpinning next-generation initiatives. Machine learning and artificial intelligence algorithms are incorporated to sift through massive datasets, identify rare event signatures, and optimize detector performance. Advanced Monte Carlo simulations model particle interactions and propagation with greater fidelity, integrating cosmic ray physics across multiple scales. International collaboration plays an integral role, pooling resources, expertise, and data across observatories worldwide through networks such as the Global Cosmic Ray Observatory, GCOS. These synergies maximize scientific return, reduce systematic uncertainties, and foster coordinated multi-messenger campaigns that observe the universe simultaneously through cosmic rays, neutrinos, gravitational waves, and electromagnetic signals. Furthermore, experimental efforts increasingly intersect with theoretical research, advancing cosmic ray acceleration models, transport theory, and high-energy particle physics. These integrations guide observatory designs and data interpretation, ensuring that observations confront and refine underlying physics. Finally, the human dimension. The training of a new generation of astrophysicists, engineers, and computational scientists is fundamental to sustain progress. Education initiatives, public engagement, and interdisciplinary collaboration ensure that next-generation cosmic ray research remains vibrant and innovative. In sum, the tools for the future exemplify a synthesis of cutting-edge technology, cutting-edge science, and visionary collaboration. As these observatories come online and research endeavors unfold, humanity edges ever closer to decoding the full narrative of cosmic rays, from their origins and journeys to their cosmic consequences. With this momentum, Our exploration progresses towards understanding cosmic rays within theoretical frameworks and simulations, probing how these particles influence cosmic environments across scales and epochs. A journey from the minute world of particles to the vast structure of the cosmos itself. As our understanding of cosmic rays deepens through observations and experiments, it becomes increasingly essential to complement these empirical insights with robust theoretical models and sophisticated simulations. Cosmic rays traverse complex environments, undergo intricate interactions, and influence cosmic structures over vast scales. Capturing these multifaceted processes in theory and simulation is crucial for interpreting data, predicting phenomena, and probing the fundamental physics underlying cosmic ray behavior and impact. Theoretical modeling of cosmic rays involves various interconnected domains: acceleration mechanisms, propagation through turbulent magnetic fields, interaction with interstellar and intergalactic media, and feedback effects on astrophysical environments. These areas require integrating plasma physics, high-energy particle physics, magnetohydrodynamics, and cosmic structure formation into comprehensive frameworks. At the core of acceleration modeling are shock waves generated by supernovae, active galactic nuclei, and other energetic events. Diffusive shock acceleration theory, grounded in the Fermi acceleration mechanism, mathematically describes how charged particles gain energy by repeatedly crossing shock fronts, scattering off magnetic inhomogeneities. Numerical simulations solve kinetic equations and magnetohydrodynamic (MHD) equations to quantify particle energy spectra, spatial distributions, and acceleration efficiencies, accounting for non-linear feedback between accelerated cosmic rays and shock dynamics. Modeling cosmic ray propagation addresses how these charged particles diffuse, scatter, and lose energy as they navigate the tangled magnetic fields of galaxies and the broader cosmos. Propagation codes implement transport equations incorporating diffusion coefficients derived from turbulence theories, energy loss processes, such as collisions and radiative interactions, and nuclear spallation. These simulations predict spatial anisotropies, chemical composition changes, and spectral features measurable by detectors. Sophisticated cosmic ray propagation models often couple with galaxy and cosmological simulations. Incorporating cosmic rays into MHD and hydrodynamic cosmological simulations reveals their influence on star formation regulation, galactic winds, and circumgalactic medium thermodynamics. This approach elucidates the role of cosmic rays as agents of feedback, shaping galaxy evolution and large-scale matter distribution. On the particle interaction front, simulations employ Monte Carlo techniques to model air showers produced when cosmic rays collide with Earth's atmosphere. These simulations track billions of secondary particles cascading through the atmosphere, predicting measurable quantities such as particle densities, energy deposition patterns, and Cherenkov and fluorescence emission. Accurate modeling of high-energy hadronic interactions, informed by collider data and theoretical extrapolations, is vital for interpreting ground-based cosmic ray detector signals. Beyond astrophysics, theory and simulation of cosmic ray interactions explore fundamental physics, including tests of particle interaction cross-sections and searches for physics beyond the standard model. Simulating exotic scenarios, such as dark matter annihilation producing cosmic rays, offers insights bridging particle physics and cosmology. These modeling efforts depend heavily on computational advances, benefiting from the exponential growth in processing power, parallel computing, and machine learning algorithms. Artificial intelligence techniques increasingly assist in parameter estimation, uncertainty quantification, and pattern recognition within simulation outputs and observational datasets. Collaboration across international scientific communities fosters the development of standardized simulation tools and open-source platforms, enhancing reproducibility, transparency, and data sharing. Projects like CR-PROPA for extragalactic propagation and Corsica for air shower simulations exemplify such collaborative initiatives. Ultimately, theory and simulation provide indispensable lenses through which the empirical complexity of cosmic rays gains clarity. They enable not only interpretation of observations, but also prediction of novel phenomena and guidance for future experimental design. Our next chapter expands this understanding by synthesizing cosmic ray impacts across micro to macro scales, from influencing individual particles and molecules to shaping galaxies and cosmic evolution, underscoring the pervasive and profound role cosmic rays play in the universe. Cosmic rays, though minuscule particles traveling at near light speeds, wield an influence that extends across an incredible range of scales, from the microscopic interactions within atomic nuclei to the vast structures governing galaxies and the intergalactic medium. This remarkable ability to impact phenomena from the tiniest to the grandest scales underlines their role as pivotal agents in shaping both the physical universe and its evolutionary pathways. In this chapter, we unravel how cosmic rays imprint their presence across these diverse scales, weaving a continuous narrative that links particle physics, astrophysics, chemistry, stellar dynamics, and cosmology. At the microscopic scale, cosmic rays initiate a cascade of interactions as they collide with atoms and molecules. These particle collisions produce secondary particles, ionize atoms, and generate radiation fields, serving as catalysts for chemical reactions. Within the interstellar medium, such ionizations drive complex astrochemical networks, facilitating the synthesis of organic molecules and altering molecular cloud chemistry, essential for star and planet formation. This micro-level energy deposition thus acts as a trigger for large-scale chemical evolution, setting the foundation for the emergence of life-supporting environments. Stepping up to the scale of individual stars and stellar systems, cosmic rays influence stellar atmospheres, magnetic fields, and even the progression of stellar life cycles. They modulate ionization in protoplanetary disks, alter magnetic coupling, and affect stellar wind properties, thereby impacting star and planet formation processes. In compact remnants like neutron stars, cosmic ray populations themselves become entities of study, revealing insights into extreme physics and particle acceleration. On the scale of planetary environments, cosmic rays participate in atmospheric ionization, cloud microphysics, and climate modulation, linking extraterrestrial high-energy events to weather and habitability on worlds like Earth. Their influence on mutation rates and genetic variability underscores their role in biological evolution and ecosystem dynamics, bridging cosmic phenomena with the biosphere's intricate workings. Expanding to galactic scales, cosmic rays constitute a significant component of the interstellar medium's pressure and energy density. They drive galactic winds, regulate star formation through feedback mechanisms, and contribute to magnetic field amplification. These processes shape the morphology and evolution of galaxies, influence gas recycling, and mediate interactions between the galactic disk and halo. At the circumgalactic and intergalactic scales, cosmic rays help regulate the thermodynamics, ionization state, and dynamics of gas reservoirs that feed galaxy growth and drive large-scale structure formation. By interacting with magnetic fields and radiation backgrounds like the cosmic microwave background, they participate in cosmic feedback loops, essential for understanding the cosmic web's evolution. The multi-scale influence of cosmic rays also facilitates a unique synergy among diverse disciplines. Particle physics models inform astrophysical interpretations, while observations across the electromagnetic spectrum and neutrino detections integrate to build a comprehensive picture. Computational simulations span scales, from particle kinetic models to cosmological magnetohydrodynamics, illustrating a nested hierarchy of cosmic ray effects. As we appreciate the bridge cosmic rays form across scales, we see that their presence is neither incidental nor localized. Instead, they are persistent agents shaping matter and energy flow, driving chemical evolution, influencing dynamic processes, and contributing to the conditions conducive to life. They serve as a testament to the intimate interconnectedness of the universe, where phenomena at the smallest level resonate throughout the largest cosmic structures. Our reflective final chapter will now consider the cumulative impact of cosmic rays, synthesizing our evolving understanding of their role in the cosmos. We will contemplate how the ongoing interplay of observation, theory, and technological innovation continues to illuminate the multifaceted influence of cosmic rays, inviting us to marvel at the complexity and beauty of the universe, shaped in part by these energetic particles. Throughout our extensive exploration of cosmic rays, we have traversed a vast landscape of scientific discovery and inquiry. From their mysterious discovery over a century ago, through their complex nature and diverse origins, to their profound influences from the tiniest chemical reactions within interstellar clouds to the grand architecture of galaxies. Our journey has underscored the remarkable role these energetic cosmic visitors play as both messengers and makers within the universe. Reflecting on the cosmic impact of cosmic rays, it becomes clear that our understanding of these particles has evolved significantly, shaped by the synergy of observational breakthroughs, theoretical advancements, and technological innovation. Where once cosmic rays were mere curiosities detected as unexplained ionization, they are now recognized as pivotal components in astrophysics, particle physics, planetary science, and even the story of life itself. Cosmic rays challenge us to think across disciplines and scales, linking the infinitesimal with the infinite. They push the limits of particle acceleration, probe the structure of magnetic fields threading through space, influence the chemistry that births stars and planets, and interact intricately with planetary environments, including our own. Understanding their origins and impacts continues to refine our map of the universe and our place within it. Yet, despite remarkable progress, many questions remain open. The acceleration mechanisms that produce the highest energy cosmic rays, the definitive sources tracing back incoming particles, and the full scope of their effects within galactic environments and beyond. The mysteries of anisotropies, the exact nature of the GZK cutoff, and the cosmic rays' role in climate and biology prompt ongoing research and interdisciplinary collaboration. Importantly, cosmic rays embody the spirit of scientific exploration. They remind us that the universe is a dynamic and interconnected whole, where phenomena as seemingly intangible as charged particles passing through space hold keys to understanding cosmic history, evolution, and fundamental physics. Looking ahead, the continual development of advanced observatories, improved simulations, and global scientific cooperation promises to deepen our insight into cosmic rays' multifaceted roles. The integration of multi-messenger astronomy, leveraging cosmic rays alongside neutrinos, gravitational waves, and electromagnetic radiation, heralds a new era of comprehensive cosmic understanding. Our evolving grasp of cosmic rays also carries practical implications, from protecting human space travelers against radiation hazards to understanding climate influences on Earth and unveiling universal processes shaping matter and energy. In sum, cosmic rays are not only cosmic travelers, but cosmic sculptors, agents intricately woven into the fabric of the universe's grand design. As we continue to unravel their secrets, they will undoubtedly illuminate new pathways of discovery, inspire scientific curiosity, and enrich our comprehension of the cosmos for generations to come.